I guess we can start. I am Angelo Ulpiani. I am one of the organizers, and okay, I guess this is a small workshop. It's not necessary to do a long introduction to convince the audience of the relevance of the work of Boltzmann on the transport equation, and even after 150 years, this contribution is still important and an inspiration for many of us about the problem of transport and irreversibility in general. So with Stefano Marmi, Andrea Puglisi, Sauro Succi, and Carlangelo Reverani, we decided to organize this event, which, in our opinion, can be interesting for the development of the field. And now we have a small speech by Professor Malchiodi.
Hello, everybody. I'm Andrea Malchiodi, and I'm the current director of the Giorgi Mathematical Research Center. So I'd like to welcome you to this workshop on a classical but still a very challenging subject. So I will just say a few words and won't take much of your time. So the Giorgi Center was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, but with the mission of gathering somehow the whole mathematical community in Pisa. So which also includes colleagues from the university, mostly, but also from Scuola Sant'Anna. And these institutions, and especially the former, in fact, contribute financially and crucially to the activities of the center. So I'm happy that today actually have both former directors of the center, Mariano Giaquinta, the founding director, and Stefano Marmi, his successor. So the main activities of the center have been, since the foundation, mainly workshop, schools, and intensive research periods. And we also restarted recently a colloquium series. So we have visiting positions of two types, 2 years postdoctoral positions, and short time visiting positions to perform research in pairs or in small groups. So as many centers of this type were affected recently by the pandemic, quite strongly, actually. We restarted with workshops last year. There was a break during the last winter, and I hope everything will go smoothly this year. So finally, I would like to thank the organizers for bringing up this really high quality event, and also the staff of the center for their constant and precious help. Thank you.
I'm glad to be here. Thank you for the invitation. And I will talk today about the beginning of the work of Boltzmann and the growth of the ideas which led to the Boltzmann equation. But mostly I want to stress what happened before. So in 1866, the Boltzmann thought that the second law of thermodynamics could be a theorem in mechanics. And he started from the identification of the yes, but it's not so easy. Started with the identification of temperature, absolute temperature, with the average kinetic energy, which was formally stated by Koenig a little earlier. Yes. Okay. And the proof that Boltzmann starts is just the first line. He wants to show that dq over t is an exact differential. Okay, let's see if I can go. Yes. So he starts with an assumption which probably will sound very strange to most of you. At least to me, it sounded strange. And he thinks that a system in equilibrium, a gas in equilibrium or a liquid in equilibrium, is is in a periodic orbit. So the motion of the representative point of this system just goes on a periodic orbit, maybe of long period, they say, and at certain point even says perhaps it is even infinite, but that is a parenthesis which is not very much pursued. So the fundamental hypothesis is that the motion is periodic, and the averages of the observables are simply computed by integration over time, over the period. The period is called I, for perhaps not what you would expect, but I is the name for the period, and this supposes that the system is subject to interaction, which is conservative, with potential V for the interparticle potential and an external potential. The external potential is eventually set to equal to 0 in his paper, and that was the source of the controversy with Clausius, who said that the important thing was not to put the external equal to 0. Okay, but the idea of Boltzmann, I think, was very interesting, nevertheless. And so his problem is to consider the variation of the averages of the observables when an equilibrium state changes from x plus to x plus delta x. And that is, non si sente? Sì, vabbè, scusate. Okay. So he wants to study this. I think that it is worth spending a few words on this proof of Boltzmann, which is not very well known, and actually it is extremely difficult to read. Both in the version of Boltzmann, it's less difficult in the version of Clausius, which is much later, and then still deals with a strange assumption, which I'm sure many of you will find strange. I certainly did find strange. So I spend a few words on this argument of Boltzmann. Yes. Come volete? Okay. I'm sorry. Task. Spero che così sia meglio. Io sto comodo, siete voi che non state. No. Va bene così? Si sente meglio? Ah, vabbè. Allora, quindi posso camminare. Allora, quindi il problema di Boltzmann è confrontare. Così? Ah, mi confondete. Allora, his problem is to compare the properties of the averages of the observables in two states. A state is just a periodic orbit, which are close. One is x and the other is x plus delta x. Now, the parametrization that is used by Clausius, not by Boltzmann, and that is a point which makes the whole thing much clearer. The parameterization is chosen by giving a function psi of period 1, which is the trajectory in position space of the motion of your system, which is, think of a gas, and the actual equation of motion x of t is simply psi computed at t over I, where I is the period. So you have a period 1 function and the period, which parameterize your motion. So then it is easy to compute the averages. For instance, the average is just the integral from 0 to 1 over the phase. That's the name that is used, phi, if the observable depends only on the positions. If it depends also on the velocities, then I enters in an essential way in the value. For instance, the average kinetic energy is the first derivative square of psi integrated, and so you get an explicit dependence on I. Okay, this is important to remark this, because when you take the variation of the observable of the motion, if the observable you're considering depends only on the configuration of the system, then it is just an integration over phi and does not see I. So, I say that delta V bar is delta psi V bar, whereas delta K bar is different. It has the variation. It has the variation of the average of K if you change the trajectory psi, but it has a contribution from the variation of the period, which is delta I over I, because the derivative of 1 over I square is minus 2 over I cube, and therefore you get this extra term here in the variation. Okay, so this is just the formalism. Now the key remark is that the variation of the average value of K plus V, so the variation of the total energy, is equal. Well, first of all, trivially, it's decomposes in this way, and then you have the idea that this is the variation of the internal energy, du bar, and this is the work that the system performs over the outside, and you call it dl. And so, if you remember thermodynamics, it's natural to say that this sum is the amount of heat that the system has received. And this innocuous remark leads immediately to the theorem, because delta Q, as I said, is the variation of the total energy, is equal to the contribution from the variation of the period plus the contribution of the variation of the orbit. And if you are exercised in mathematics, in mechanics, you see that there is something wrong in the first line. You would like to have not K bar plus V bar, but you would like to have minus K bar plus V bar, because that would be the action. So you just change the sign to K bar and compensate with the other term, and then you are happy, because the variation of a fixed period of the value of the action is 0. That's Maupertuis principle, right? So the conclusion is that delta Q receives only contribution from the first two terms. However, the term 2 delta psi K bar is not nice, because it's not a variation. It's a variation only of the orbit. Okay, then you just use again the first line and change delta psi K bar into delta K bar, and this changes the sign in front of that, of the first term. Okay, that's it, because now you divide delta Q by K bar. It's here. The first term gives this, and the second term gives that. And that is just the variation of the logarithm of I K bar. And that's the formula for the entropy in Boltzmann and Clausius works. So it's an exact differential. So that is the theorem of Boltzmann and of Clausius. And now let me go on. So Boltzmann says that, therefore, one sees that the first principle of thermodynamics is essentially the energy conservation, and the second principle instead is the action principle, right? Because that has entered in an essential way in the derivation of the formula. Okay, now should it be assumed that Boltzmann Clausius, Maxwell, were really believing that the motions would go through all points of the energy surface in a periodic fashion. Okay, you can. I don't think it is possible to think so. I don't think that they were believing that you could really visit a continuum in 2 dimensions, but with a non-self-avoiding line in 1 dimension. Yes, in 1 parameter. Okay, for instance, usually people insist in saying that that's what they were believing, and for instance, I just put one of the quotations to which one refers by Maxwell in 79. Now, this date is important, as you will see in a moment. Yes, one could think that one really, after a sufficient number of collisions, the motion will pass through every point in consistent with the equation of energy. Okay, but I don't think that that is the real thing. Boltzmann has done many places in his work. He puts up a philosophical view that what is really that continuum is an abstraction, and for instance, he says that the derivatives are just limits of differences, and that's the key point is the difference, not the differential of the function. He insists many times. He says in different ways that one should think in discrete terms, whatever one does in analysis. And I completely agree with this thing personally. And okay, but the question was, this was 1866. Soon Boltzmann was worried was worried less by periodicity assumption, and he was concentrating himself in describing the stationary states of the system, whether or not they are periodic. That is something which was in the background, but it was not the main point. So at the same time, he had a controversy with Clausius about priority, and that is it was a secondary interest of Boltzmann, I believe. What is very important is the breakthrough work of '68, where it's a long paper, extremely difficult to read, not only because it is in German, but mainly because of the density of formula and of statements that is there. But in the last section of the paper, he says that finally I shall establish a general theorem of probability on the probability that consider the point masses occupy distinct locations and velocities. That's a statement. It is asking what is the probability distribution of the positions and velocities simultaneously of all particles in a gas. Okay, forgetting periodicity, and that's important. The key assumption is very interesting. He supposes that this distribution of the locations and velocities of the particles is a function of phase space, f of pq, and this function is a smooth function. Correctly, as I said, Boltzmann was not very fond of differential analysis, strictly speaking. Of course, he knew it and he used it, but he really I don't think it occurred in his mind that there might be a non-smooth function which describes the positions and velocities of the particles. what the ergodic, the visitation of all points of the energy surface is only used in the sense that if the motion density covers the surface of energy, then the function f of pq, which has to be invariant under time evolution, because you are studying a stationary state, is smooth, and therefore, being smooth on a dense set, it has to be a constant. Okay, because of the Liouville theorem guarantees that if f is constant, then it is a stationary distribution. So I wrote this implicing strongly because this is the point to discuss. Maxwell comments in '79. This is a very important paper of Maxwell. Is probably the last paper of Maxwell, or perhaps the one before the last, because he died soon after. And it's a paper in which it really entirely dedicated to the '68 work of Boltzmann, which is, as far as I know, I have met very few people who are aware of this paper. But that is, I think it's probably the most important paper of Boltzmann, or at least among the most important. So Maxwell will comment on this paper. Okay. No. Yes. So why, if f is smooth and invariant under evolution, it has to be a constant. Well, the point is that you look for a smooth function which is invariant under time evolution, and this says that whether or not we are able to prove that the constancy of this function is a necessary condition for a steady distribution, it is manifest that if I assume that f is a constant, then this is a solution to the problem of finding a stationary state which has a well-defined smooth distribution which describes it. It is a solution, but if not the only solution, it is at least a solution. Boltzmann in '68 was not aware of the fact that there might be more than one solution. So having found one invariant distribution which is smooth, he was happy, and from that he derived the microcanonical ensemble, which is also something that usually is not attributed to this time of the 1800s. Furthermore, in the paper, he divides. Once he knows that the distribution is a constant, he computes what is the actual value of the probability of finding positions P and Q in phase space, and he does this by the familiar counting argument. He divides phase space into cells and counts how many, and that's the familiar counting argument, which is usually attributed to a later paper of Boltzmann, in which he was again doing this calculation, and okay. So he gets this, in modern language, he gets this formula. In fact, he gets separately the Maxwellian distribution in the P's and the macrocanonical distribution, which is the integral of this function over the P's. But he clearly has everything. He only points out these integrals of this function f. It's important that this is for all particles and with an arbitrary potential of interaction. Okay, so he was very happy about, probably he was very happy about this result, rightly so. And the next problem that he takes, find an example. He wants to find an example of a system which has a trajectory which invades densely the whole energy surface. Okay, and he writes a paper on that, and which is interesting, but the conclusion is not correct because you can see in this paper number 7, and which has even been proved mathematically in a subsequent paper by Giovanni Felder, that the system is not does not go and does not evolve in such a way that the trajectory covers densely the energy surface. That's an interesting fact about conics, incredibly, but it was not correct. Nevertheless, it was very important, a very important paper, which is vastly unknown. People don't. The paper is titled "Solution of a Mechanical Problem," and I eventually found one person who read it, but it's not well known. But it's interesting, and the whole point is that Boltzmann, one could say with our present-day knowledge, Boltzmann thought he had an example because he did not have what we know today as H-theorem. It's a property of the Hamiltonian systems which are close to integrable. Not knowing that, it is fairly reasonable to believe, to think that you may have an example, but then it is not true. But still, one can say that if you push the parameters of the system of Boltzmann conveniently, you find at least chaotic motions enough to be confused about the question whether that is an example or not. Now, after the paper of 68, Boltzmann writes a few papers which draw conclusions from this work. There are 3 papers in 71, which I call the trilogy, and he starts applying the ideas of 68, and he became very concerned about the fact that as the example, this example that I just mentioned, which is not correct, strictly speaking, really shows that Boltzmann did not yet conceive the existence of possible other probability distributions which are smooth and have positive density on phase space. Right. Just parenthetically, I say that one of the modern definitions of an ergodic system is that, which is Hamiltonian, is that there is only one invariant distribution which has a density, and it is the constant. That is the modern definition of the ergodic hypothesis. Okay, so he did not conceive that there could be others. So as soon as he found one, he was happy because he was able to use it for. But this was before 71. In 71, he realizes that there is a problem about this question and stresses it, and does not solve it because, as you know, it has remained as an open problem until recently, and even recently it has been understood only in few cases.
Paola,
Okay.
se vuoi puoi anche spegnere, eh?
Non sono io, eh? Va bene. Okay, so in the first of the 3 papers, it shows that a single molecule in a gas, in a rarefied gas, as the particles in the molecule, so the few particles in the molecule obey the the microcanonical distribution, and it does this without using the periodicity, but just exploiting the invariance properties. So the fact that the distribution, if it exists, it has to be constant over the energy surface. And that was the idea of the previous paper, and it just applies it to a single molecule in a gas. And the central theme in Boltzmann emerges clearly already in this paper, that the equilibrium distribution is supposed to have a density in free space, which is smooth, and the symplectic symmetry guarantees that the volume is conserved, and therefore you have an example of such a distribution. Now, if the trajectories are dense in phase space and the distribution is continuous, it has to be a function of the energy invariant. This was implicit in the 68 paper, and it's still used in this present work. In the second paper of the 71, he again realizes that there is a problem with the uniqueness of the smooth distribution on phase space, and adds as a supporting assumption the fact that there are not multiple collisions, as the presence of multiple collisions confuses the issue of the constancy of the distribution, and it just adds it as an assumption, and this led to consider a large number of copies of the system, which is thought of as a giant molecule, and but does not interact with anything else. So it constructs a large number of copies of the system without reciprocal interaction, and density of trajectories in phase space is still taken for granted, but you cannot. Its dependence on the only energy is explicitly questioned, and the absence of collisions is added as an assumption. And in the third paper, he introduces the notion of thermodynamic analogy. He says that if the set of states of your system is just a collection of probability distributions on phase space, if you change some of the parameters, so that you go from one distribution to one which is close by, and define the dq amount of it received as the sum of the variation of the internal energy plus the work the system does on the outside, then if within this family of distributions, it is true that the quantity dq over t is an exact differential, then by definition you have a model of thermodynamics. And it gives, as an example, the microcanonical ensemble, and all these things sounds like Gibbs' work, but Gibbs himself, in the introduction of his book, he acknowledges that this idea is already in Boltzmann. Okay. The next step in the Boltzmann development was that of proposing the Boltzmann equation. Now, this is a very interesting contribution, of course, and which allows to determine the macroscopic equations obeyed by gases. But these are only rarefied gases. That's essential. And in this respect, it is interesting to read the 79 paper of Maxwell, which I already quoted, which is one of the last in his life, entirely dedicated to comment not the Boltzmann equation, but the 68 paper of Boltzmann, which is the first one, the second one I was quoting in the beginning. And but in the long and detailed analysis, celebrating the Boltzmann paper of 68 and clarifying it, because it's much easier to read the Maxwell version than Boltzmann himself, old paper. It does not even quote the Boltzmann equation, the 72 paper, which is the well-known paper on the Boltzmann equation. And he states that the treatment of Boltzmann of the 68 paper, in which he derived essentially the microcanonical distribution under the assumption that the distribution is a smooth function on the energy surface, and the trajectories are dense on it. He says that the treatment is ingenious, okay, but it's better to revisit it so that other people understand better this fundamental result. Okay, so it is really interesting to read this paper, by the way. So the natural question at this point is that did Maxwell overlook the contribution of the Boltzmann equation? Now, you can think yourself what is the reason. I think a possible explanation is that he had greatly contributed to the theory of gases in his work on for instance, on the dynamical theory of gases of 1866, which is a major contribution motivated by his interest on the nature of viscosity. Maxwell had built a general theory of rarefied gases and their microscopic properties via the study of the evolution of various observables under the influence of the Hamiltonian dynamics with R⁻⁵ potential, which was not really essential. That was essential only to make simpler the calculations, and he believed that this R⁻⁵, because of its nice properties, would be a special law, which did not turn out to be the case in subsequent works. But that was not important. The important thing was that the evolution of the various observables under the influence of Hamiltonian dynamics was studied in the frame of rarefied gases, and it was deriving the macroscopic properties of this. Now, in each case, in Maxwell, the evolution was studied via the analysis of collisions and their scattering properties. The techniques and results were exactly the same. If you read the paper of Boltzmann, it's impressive. Maxwell, it's impressive. The techniques and results were exactly the same that would be obtained in each case. He considered many cases, studying viscosity, studying fluid equations and general properties of this type, and they would be obtained simply by taking the Boltzmann equation and multiplying both sides by suitable observables, and then you derive the results that we are now used to derive from the Boltzmann equation itself. So, in other words, Maxwell had developed much earlier than Boltzmann a weak version of the Boltzmann equation in mathematical language. So, you don't write the equation, but you write what would be the value of the integration of the two sides of the equation with respect to some observable of interest, and use the conclusion to derive the properties which can be even experimentally tested in some cases. So Maxwell, I think correctly felt that the paper of '68 was the main breakthrough of Boltzmann, because it solved the problem of giving a probability distribution of the microscopic states, and that is the basis of statistical mechanics. The H-theorem was a synthesis of over many studies clarifying the reversibility phenomenon, and with time, it exercised essential influence to extend the role of entropy of modern studies on stationary non-equilibrium, which is dominated nowadays by the role of strange attractors and chaotic motions, and essentially dominates also our modern understanding of irreversibility, as we shall see in the coming talks. So I think after this, in case you want to check the statements that I have made, I have collected a few references, which I think they are available to the people in this. There are quite a few references. So I think this is what I wanted to say as an introduction to Boltzmann.
There is a question regarding the discreteness. Can you say that also? Thank you so much. I said I learned a lot from this talk, many things which were new to me. Regarding the fact that Boltzmann was not fond of continuum.
Yes.
Did he have any estimate for the size of the discrete cell in phase space? What would be nowadays H bar?
I don't think he really discusses this point. He just says that if you want to understand whatever in physics, you don't need the different analysis. You only need to know the addition and subtraction and multiplication. And he says this explicitly. But yes, it should. He uses the discreteness explicitly already in the '68 paper, where he derives the value of the number of atoms which are in a cell in phase space. He uses what we do today. I mean, in the course of
it was very modern.
Yeah, that is extremely modern, and it is in '68. However, as far as I know, at least the references that I have found to this point refer to this 1877 paper, so after the Boltzmann equation, in which he again does this calculation for these and other reasons, but that was already in '68. He certainly was doing a calculation by counting numbers, right, with factorials and everything.
Actually, as a side remark, I recently realized that in his book, Vorlesung über Kinetic Theory, he writes explicitly that even the velocity should be taken discrete, because this is a much more physical way of computing things, which was quite remarkable, I would say.
Oh, but for instance, in my book on statistical mechanics, there is an entire section of quotations of Boltzmann on discreteness. So I am definitely on his side. I never understood why one should take limits. But
that's interesting. Thank you.
Other question? So, I mean, I was surprised that I did not know. I mean, the fact that you start with the periodic motion.
Yes.
On some sense, I mean, the Boltzmann equation is based on the instability of mechanical systems.
Yes.
So there is a sort of contradiction in a sense. Can you comment about that?
But that is only for rarefied gases. So you are unhappy about what? About the fact that the Boltzmann equation foresees.
I mean, Boltzmann equation works because the mechanical systems are unstable.
Yes.
Otherwise,
no, but you see, this periodic business is in the first paper of 1866, and then essentially it is forgotten. What really remains is that the motions cover the energy surface, and therefore the distribution has to be constant, being smooth. And the whole problem is that smoothness is an essential. It is the modern definition of ergodicity. It is precisely that there is only one smooth distribution, which is invariant. Not always true, and difficult to prove when true.
Again, about the periodicity, can you say something about the connection of this idea of periodicity and the Helmholtz monocycle approach? In some sense, the similar idea, no?
That is much later.
Yeah,
it's in the 80s.
Later, yeah.
Yes. Let me see. Boltzmann writes a paper in 84, attributing to Helmholtz many things which he had done before, by the way. And my conjecture was he had been on by
and his boss was
and he did not want to say he had already done something. Now, monocycle system.
So,
yes, I know. I'm trying to remember what I want. Yes, the monocyclic systems were examples. Were supposed to be examples. Yes. So, if you assume that your system is monocyclic, and the examples were simply, for instance, one-dimensional systems, which are integrable.
Yeah.
For these systems, you build a collection of probability distributions which are concentrated on a single orbit,
yeah.
Right? And which have the property of this that I mentioned.
Possibility to introduce the entropy, which
it is possible to introduce studying the variation of the observables. You can define the amount of it in a change of state, and the amount of energy, and so on, in such a way that the Q over T is an exact differential. And then that's a model of thermodynamics. Yeah. And that was the idea of Helmholtz, that this could be general. And yes, but it applies only to systems which are, but Boltzmann in his paper says, these are examples of a general fact, collection of distributions, which such that the variation of the observables between one and one, close by one are such that the quantity that you interpret as dq over t is an exact differential. Right. An example that Boltzmann gives is the Saturn rings. So a stone in a Saturn ring provides you with an example of a thermodynamic system, but that is too special in a way if you take it for the Saturn ring. But if you take it for a general system, you have this notion that was due to the paper of 71, in which you have the general notion of model of thermodynamics, which is actually what is used in statistical mechanics today.
Other question?
Can you comment on the last sentence you wrote about the connection between the H-theorem and the strange attractors?
Yes, the modern irreversibility. Yes, you know, it is. What is the definition of a strange of a system which is a chaotic motion and which is nice, right? For Hamiltonian systems, we say that it is nice when it is ergodic, so when there is only one smooth invariant distribution. The key point, in my view, of modern theory of irreversibility is just the extension of this idea, which is the natural distribution, the unique distribution which describes the statistics of the motions that you observe. And that is, it is essentially due to Ruel, who says that whether the system is Hamiltonian or not, as long as it is chaotic, and for that you have, well, you know what it means, but I don't give a definition because it would be difficult. Provided it's chaotic, then there is only one distribution which describes the statistics, and that is not the one which is absolutely continuous, which has a density on phase space, because we know it's not the case. But it is the unique distribution which is obtained as a limit of initial data which are chosen with a smooth distribution of phase space. Whatever the smooth distribution you use, you reach always the same stationary state, and that is the one that has to be used to study the statistics of a reversible or irreversible stationary state. And I think that this is not again, it's one of these things which are not fully appreciated in the community which I meet. This is considered as a mathematical curiosity, but it is a basic principle, as basic as the one that in equilibrium you have the microcanonical distribution as the only possible distribution which describes the stationary states, provided the Hamiltonian system is chaotic. That's in parenthesis, which you know, it is a big parenthesis, but still. So this is the comment. And this originates from the fact that Boltzmann was, you can think it originates, at least it relates to the fact that Boltzmann was thinking that there is, that the distribution visits the old surface, and therefore it has, if the system is Hamiltonian, therefore it has to be the constant distribution. So
the strange attractor is finite dimensional.
No. The chaotic system is supposed to have a strange attractor, and typically it's unique. But you have to agree on what you want to call chaotic system. But the definition is like in Hamiltonian mechanics. It's not true that all Hamiltonian systems have the one distribution which is stationary, but generically it should be so. For instance, in non-equilibrium, you have the same. You have only one distribution, which is, well, you have finitely many possible distributions, because you have typically out of equilibrium the phenomenon of intermittency, and intermittency simply means that you have a lot of attractors, right? And each of them has a unique distribution, but you have to know on which attractor you fall, and that is difficult because the attractors have common boundaries. The domains of attraction have common boundaries, and if your motion goes too close to a boundary,
you are outside the H-theorem, so in the non-equilibrium situation.
Outside, okay. Completely outside. Now, the H-theorem is interesting, and it appears also in the theory of chaotic systems through the variational principle, which is obeyed by this unique distribution that attracts the motion, whether you have one attractor or more. But once you concentrate, you're able to concentrate on a given attractor, which is not so easy when the system is intermittent. Then the stationary state maximizes a certain quantity, which is essentially the analog of the entropy in equilibrium. Yes, I think this is a fundamental contribution of Ruel, which has probably still has to be appreciated enough.
Other question? Okay, we have a lot of time for the coffee break, and maybe we can continue the discussion during the in a more informal way. We start at 11:15, so we have a very long. So the second chairman of this section, Silvia Lorenzani.
Grazie. Okay. Thank you. Okay, I can introduce myself anyway. Thank you very much. First of all, I would like. Okay. But first of all, I would like to thank the organizer for this kind invitation. It is a great honor for me to be here. And okay, and I recognize that is an undeserved privilege for me. And so thank you very much once again. And I will speak about the possibility to obtain a variational principle for the linearized Boltzmann equation. This variational solution of the Boltzmann equation was a very popular method, especially in the 60s, because the computer resources were limited at that time. So a lot of people try to find analytical or semi-analytical solution to the Boltzmann equation. And originally, this method was developed for the linearized Boltzmann equation in the integral formulation. Imagine to have a linear operator L applied to the unknown distribution function H and the source term S. Now, let us assume that L is self-adjoint with respect to a scalar product that for the moment we will not, is a general. And then one can introduce a functional J of this test function H tilde. And one can prove that if we set a H tilde equal to H plus eta, where eta is a small error, the term linear in eta disappear from J, and therefore you can reach, you can write equation 3, and of course, and H is the solution of the true Boltzmann equation. Now, so this variational principle was very useful and say that practically this functional J is stationary corresponding to the true solution of the Boltzmann equation. And of course, if you then know that the last term on the right-hand side of the equation 3 is a well-defined sign or positive or negative, you can even say that the solution of the Boltzmann equation corresponds to a maximum or a minimum of your equation. But even if you do not, you cannot, as in general, it happened that you do not know the sign of this quadratic term in eta, this method is also very useful because it gives to you a non-arbitrary receipt to select among approximation to the solution of your equation in a given class. And moreover, if you usually one can prove that J is related to a physical quantity, a quantity of physical interest. Therefore, even if you have a poor approximation of your test function, you can compute this physical quantity with high accuracy. But the formulation, as I said at the beginning, the formulation that I present in equation 1 is usually what's written corresponding to the integral formulation of your equation, and the integral formulation can be written in closed form for essentially for the simplified kinetic model, like for example, as for example, the but assume, if you want to use the true linearized Boltzmann collision operator, you have to split your collision operator in two parts. So you have to approximate further the collision operator, and moreover, you have to use you have to change your functional changing the problem. So at the end, in this formulation, the variational principle was not very useful. So in 1969, Carlo Cercignani wrote a paper published in Journal of Statistical Physics. And in this paper, he introduced a new variational principle that could be applied to the integral differential equation, to the Boltzmann, the integral differential Boltzmann equation, and not any longer only to the integral version of this equation. And therefore, this variational principle could be applied, of course, for every collisional operator, considering also a general interaction potential between the molecule, and also but I cannot, no, it's fixed to this slide, I cannot going on. Okay, thank you very much. And this new variational principle introduced by Cercignani could be applied to extremely general collision term and also boundary condition. Now, in this formulation, this new variational principle could be again applied to the linearized Boltzmann equation. So you can write your unknown distribution function f as a small perturbation h with respect to the equilibrium state represented by the Maxwellian f0. And then you can write down this steady linearized Boltzmann equation in symbolic form, as I wrote in equation 6, where LH is the linearized Boltzmann collision operator, the general Boltzmann collision operator, as is a source term, and D, the differential operator. So and of course, since now the equation is written in integral differential form, you have to consider some boundary condition that in the previous variational principle disappear, and now this is the general symbolic form to write the boundary condition. I indicate with H plus the distribution function of the molecule re-emitted after a scattering with the boundary, while I indicate with H minus the distribution function of the molecule impinging on the boundary. H0 is a kind of source term because you see that is written only in terms of the Maxwellian F0, and R is the scattering kernel. So usually the most popular scattering kernel is the Maxwell model, which assumes that a fraction of the molecule alpha, which impinges with a solid wall, is re-emitted according to the Maxwellian with the same microscopic parameter of the boundary. So same temperature, same velocity. And the remaining part of the molecule, 1 minus alpha, is re-emitted according to the specular reflection. Here, in the application that I will show you later, I will consider the most general boundary condition that at the moment has been formulated, and is the Cercignani-Lampis boundary condition, a little bit complex, but for the application that I will show you, it seems the only boundary condition that can give accurate result with respect comparing the theoretical result with the experiment. And okay, now we can define an Hilbert space and introduce two kinds of scalar product, both in velocity space and in the spatial domain omega, or on the boundary of omega. in this way. So one can say, okay, I want to reuse the same variational principle originally what I showed you at the beginning, therefore I can rename the operator, linear operator L calligraphic as the difference between the differential operator and L. But if you do that, you can prove that in this case, this formulation cannot reproduce the symmetry property. So at the beginning, I say that the basic property to have this variational formulation was to have a self-adjoint operator. In this case, this symmetry disappear because of the differential operator. And but then Cerciniani proposed the following trick. In some sense, he multiply the equation by the parity operator, what I call capital P, which means that P applied to the distribution function change the sign of the molecular velocity. C, I indicate with C the normalized molecular velocity. And of course, for any general central interaction, L commute with P. Therefore, since the linearized Boltzmann collision operator LH satisfy this symmetry property, applied to heat P does not change anything. But and then what happened to the differential operator? So in equation 12, you see that indeed, even if we apply P to the differential operator, you do not obtain exactly the symmetry property that one wants. In fact, the last two terms on the right-hand side break this symmetry. But one can prove, but these two terms, the last two terms on the right-hand side are terms defined on the boundary. So one can prove that indeed you can rewrite these two boundary terms in terms of the what I call the source term H0, and usually it's possible to prove that this scalar product involving H0 are zero. In a lot of general situations, for instance, H0 is small, is the velocity and the temperature at the wall are close to the velocity and the temperature of the basic Maxwellian around which you are linearizing your problem. And in this case, you see that you can prove the symmetry properties also of your differential operator. At this point, what you can write is to define this L calligraphic operator as the difference between PD minus PL. You consider the PS source term, and you can rewrite the with this notation. You can restart from this variational principle. But the problem of this initial variational principle is also that to be applied, you need that your test function H tilde satisfy the same boundary condition as the true solution of the Boltzmann equation H. And this is a strong limitation, let's say. Therefore, Cerciniani extended the variational formulation and introduced this new functional J, where you see on the last term on the right hand side represent a boundary term. So with this boundary term included in the functional, you do not need that your test function satisfy the same boundary condition of H. Which is the true solution of the Boltzmann equation. Therefore, and one can prove that if again you write your test function H tilde equal to H plus a small error 8, the term linear in eta disappear, and then the variational principle hold. And this is what until here we have practically the basic formulation that of the new variational principle that Cerciniani introduced in 1969. But then some problems remain unsolved. For example, how to identify a general method to derive a convenient test function, because it's true that your functional is quadratic in eta, but if you choose a test function very far to the true solution, you cannot expect to have a good accuracy of your result. Therefore, the way to choose the test function is one of the most important problems that one can face with the application of this kind of method. And then the second problem is how to compute multiple macroscopic quantities, because I say that generically that in general, one can prove that the functional J is related to a quantity of physical interest. But when you study a realistic problem, you need to compute not only one macroscopic quantity as usual, but you need to compute several macroscopic quantities. So how is possible to compute all, let's say, all the macroscopic quantities related to the particular real problem, starting only from the definition of one functional? Okay, this problem, indeed, this represents my story in some sense. This problem were addressed in a series of papers. The first, the paper in blue, in some sense, represent the answer to the first problem, how to choose a realistic, accurate test function. But these papers are related mostly with the BGK model, so the formulation of the BGK Boltzmann equation. And the last, so the first paper that I wrote with Cerciniani in 2010 tried to extend the method of choosing the test function also in the case one works with the true linearized Boltzmann collision operator for our sphere, and the same also the last blue paper that I wrote. And in this case, I try to generalize, to take into account the computation with the Cerciniani-Lampis boundary condition with, as you will see in a few moments, is enough complex boundary condition. While the last two red papers are very recent, and they concern some application this variational method applied to try to reproduce some very recent experimental result. And in fact, Rina Graur, Pierre Perrier, and Hiroshi Yamaguchi are some experimentalists. They are in Marseille, where in the last year they were able to construct this microchannel experimental tool, very powerful, because they could also check a lot of results that also in the past were obtained theoretically with the Boltzmann equation. They could prove a lot of these theoretical results also experimentally. Now, and here I want to come to this application where allows one also to compare the theoretical, the variational result with this experiment. So the experiment is very simple. You have a microchannel settled between two reservoirs, and these reservoirs are maintained at the beginning at different temperature, but at the same pressure. So what happened is that there is first a flux of gas from the cold to the hot. This is already a strange thing. a flux due to this temperature gradient from the cold to the hot reservoir. And due to this fact, a counter flow, Poisson flow, developed because in the opposite direction, because then the pressure in the hot reservoir becomes bigger than the pressure in the cold reservoir, and that sometimes a sort of equilibrium is reached when the thermal creep flow, the mass flow rate match the Poisson flow. So the flow due, the gas flow due to the gradient of pressure is called Poisson flow, while the flow due to this thermal gradient is called thermal creep. So in order to analyze from the theoretical point of view this couple problem, we consider an infinite plane channel, and we assume that the pressure is small, and we call with K the adimensional pressure gradient, and with tau the temperature gradient. So assuming a small pressure and a small temperature gradient, one can linearize the problem, as therefore the distribution function f of the gas can be written as a small perturbation h above an equilibrium, global equilibrium state, represented by the Maxwellian F0 that I introduced at the beginning, and therefore one can write down a steady linearized Boltzmann equation. As you see, you can rewrite then in equation 17 symbolic form, as we did introducing formally the variational principle in this way, where dH is again the differential operator, the source term. You see that in this case is formed by two parts, the part due to the pressure gradient and the part due to the temperature gradient, while LH is, for the application that I will show you, the exact linearized Boltzmann collision operator for hard sphere molecule. And then we consider the boundary condition. For these two problems, one can prove that this, what I call the source term on the boundary, H0 is equal to 0. So you have equation 20. And if you remember, okay, the definition of the operator K on the boundary, K is written in terms of the scattering collision term R. And as R, we assume the Cercinali-Lampis scattering the Cercinali-Lampis model, as you see, is much more complex than, for example, the Maxwell model. But the advantage is that while the Maxwell model is written only in terms of one parameter, that is alpha, that I call the fraction of molecules which are diffusing with the Maxwellian of the wall, here you have two parameters. And of course, in the Maxwell model, this unique parameter alpha should reproduce the accommodation of all the physical properties of the gas. Of course, this cannot be realistic, especially in this problem where you have both the effect of the pressure gradient and the effect also of a temperature gradient. The advantage of this of the Cercinani-Lampis model that is defined in terms of two parameters that I call alpha t and alpha n. Alpha t is the accommodation coefficient of the tangential momentum, while alpha n is the accommodation coefficient due to the kinetic energy of the molecular velocity normal to the bounding surfaces. And you see, okay, that in equation 21, H0 is the modified Bessel function of first order, of first kind at 0 order. Okay, now we have all the ingredient to construct, to apply, to use our variational principle. And in this kind of problem, the macroscopic quantities that we want to calculate are Vz, which is the Z component of the macroscopic velocity, average velocity of the gas, and Qz, which is the heat flux, again, the component of the heat flux parallel to the bonding surfaces. And of course, if you then integrate on a section of the channel, you can calculate what the mass and the heat flow rate, what I call capital M and capital Q. Now, how to apply the variational method that I present to you? First of all, one can see that if in the variational this variational functional J, you insert H tilde equal to H, so you compute your functional in the stationary point, you obtain equation 26, which says to you that in fact the stationary value of this functional is related to the physical quantity that one wants to compute, both the mass flow rate and the thermal heat. Both. And moreover, in the framework of the linearized analysis, then you can, for both the mass flow rate and the heat flux, you have both the contribution of the Poisson flow and also the contribution of the thermal creep. In fact, this in equation 26-28, for dimensionless coefficient appear GP, which is called the Poisson coefficient, which represents the mass flow rate due to the pressure gradient. GT, which is what I call a thermal creep, which is the mass flow rate due to the temperature gradient. And in the question below, you have QP, which is the heat flux due to the Poisson flow, and QT, which is the heat flux given by the thermal creep problem. And then one can indeed apply the Onsager relation, which says to you that the mass flow rate due to the temperature gradient is equal indeed to the heat flux due to the pressure gradient. So you see that indeed at the formal level, your functional is indeed related to all the quantities that you want to compute. The problem is how to do this in practice. Oh, before to speak about the choice of the test function, I will introduce in some sense the why from the applicative for the application this calculation is very important. Because this calculation is very important in what is called the microfluidic. In this last decade, a lot of micro devices were built and used everywhere, practically. And of course, when the characteristic dimension of these micro devices are of the order of macro, also nanometers. And there, the properties of the property of the gas are very different from the properties, for example, of the gas in this room. But since the kinetic equation are very difficult to be solved, even from the numerical point of view, people wanted to going on in using Navier-Stokes, for example. So a lot of researchers try to study how to modify, in some sense, the Navier-Stokes equation in order to apply this equation also at least in some cases also in these micro devices. One of the best choice is, of course, try to modify the boundary condition, because what happened in these micro devices is that the gas inside is very rarefied. Therefore, the collision between the molecule and the solid wall happen more frequently than the collision between two molecules. So the interaction of the molecule with a solid wall are more important than the interaction between the different molecules. Before, the most natural way to modify the Navier-Stokes equation is to change the popular no-slip boundary condition associated to the Navier-Stokes equation with the slip boundary condition. And here I reported the two formulations of the first order boundary condition associated to the Navier-Stokes equation. The first one is related to the case when you have a pressure-driven flow. Well, this sigma P1 is what is called a viscous slip coefficient. The second equation is the formulation of the slip velocity associated with a thermal driven flow, and in this case I indicated with the sigma T1 the thermal slip coefficient. Now both this coefficient, as I will show you, can be calculated by performing an asymptotic limit of the solution for this couple problem that I present to you, the Poisson and the thermal creep. Now, before to do that, the main point is how to choose the test function. So the idea that we had is to restart from this equation, and instead to immediately apply the Boltzmann equation with the true linearized Boltzmann operator, use for LH the BGK model, that one of the most popular, this one. And the advantage, as you see, that the BGK model can be written in terms of the three microscopic fields: the density rho, the average velocity v, and the average temperature capital T. Now, of course, one of the main advantages in using the BGK model is also to be able to reduce the dimensionality of the molecular velocity space. In fact, for example, for the problem that I show you, there is only one spatial variable, the dependency on x, which is the variable along which give the distance between the wall of the channel. But of course, therefore, the distribution function h depends on x, only on x, but on all the three components of the molecular velocity c. And this is not convenient either if we want to solve analytically the Boltzmann equation or by using a numerical tool. Therefore, what usually one does is apply what is called the projection procedure in order to reduce also the dimensionality of the molecular velocity field. In fact, if we use this BGK Boltzmann equation, multiply by both sides by this factor 1 over pi Cz a to the minus Cy square plus Cz square, and integrating with respect the two components of the velocity field that we do not care, Cy and Cz, one can rewrite the Boltzmann equation, the BGK Boltzmann equation, in terms of this reduced distribution function capital Z, which now depend only on x and cx. But unfortunately, since in this, and this for some problem, this is enough. But unfortunately, in our case, we want to compute several macroscopic fields. Therefore, if you come back to the definition that I introduced, yes, Vz, Qz, you see that you can rewrite Vz in terms of this reduced distribution function capital Z, but you cannot do the same for Qz. So introducing only this capital Z distribution function, you are not able to compute also the heat flux QZ. Therefore, you can going on in applying the projection procedure to your original BGK Boltzmann equation. You can multiply again both sides for another factor, CZ divided square root of 2 pi, etc., etc., and you obtain another equation to be associated to the first one. And this second equation is written in terms on another reduced distribution function, which is capital Y. And now you see that in terms of capital Z and capital Y, you can be able to rewrite both the macroscopic field that you need. The average velocity field and also the average heat flux field. Then you associated to these two equations. So indeed, one can ask itself what is the advantage if you, instead of one equation you have two, but indeed there is an advantage, as you will see, but also from the numerical point of view, it's better to have two equations with a low dimensionality of the unknown instead to have only an equation with a lot of variable. And in this case, okay, you can assume a diffuse scattering. We say that it's not important to define a test function with the same, which satisfy the same boundary condition of the true solution, because you have a part concerning the boundary condition only also in the functional. So you can try to derive the test function satisfying other different boundary condition with respect to the boundary condition that we want to use. And in fact, we use the simplest case. So we assume that all the molecules are diffused by the boundary with the same, with the Maxwellian, with the same macroscopic parameter of the boundary. And at this point, you can integrate these two equations formally along the trajectory of the molecule. And you obtain two solutions. And from this solution, you can construct now your test function in a very accurate way. And the advantage is also the following, that is that if you started from the original equation in terms of H, you have to try to understand an answer, derive an ansatz for the test function H tilde. And it's very complex because here, practically integrating the equation along the trajectory of the molecule, here you have already given the dependency on the molecular velocity. And what you have to simply do, if you look at equation 43, is to give a test function for the only macroscopic field which appear. And it's much easier to give an ansatz for a macroscopic field instead of the distribution function. And in fact, for example, we assume as test function V tilde Z a parabolic profile, which is the solution of the Navier-Stokes. Then you, A and C are two constants that should be varied in order to find then at the end the optimal value of the functional, the minimum of the functional. So if you insert these ansatz on the macroscopic field inside here, you obtain this Z tilde, which is your test function. For the second one is even simpler because no other macroscopic field appears, so you can integrate directly this expression and find Y tilde. And then from this Z tilde and Y tilde, reconstruct a test function for your H tilde. Now, since, and this is the general method that we usually apply in order to define an accurate test function. So starting from the solution of the BGK Boltzmann equation, that since this simplified model give to you the possibility to integrate then the equation along the trajectory of the molecule, you are sure that your final solution is enough accurate. But in our case, but you see that especially Z tilde is very complex. But for our HIME, for the application that I want to show you for the derivation of this slip coefficient, we need only, we say, the asymptotic solution. Therefore, from this Z tilde, I neglected all the exponential term that disappear in the near continuum limit, because the exponential term are give the structure of the Crucial layer, which are some layer around the solid wall, a very strongly non-equilibrium layer around the solid wall. And these Crucial layers are usually of the order of some mean-free path. And if you consider a large channel, these Crucial layers are negligible. Of course, if you consider a very rarefied gases, you have to take into account. But our aim here is to derive this slip coefficient, and therefore we could neglect this exponential term from our solution and to write down this test function. Indeed, we then improve further, adding another constant in the last term, because for the following reason, everyone knows, because also tried and proved that the BGK cannot reproduce accurate result when you have flow due to the temperature gradient. Therefore, tau is the gradient of temperature, and in order to overcome this limitation of the BGK, we will put a constant that at the end should be varied in order to obtain the optimal value of our functional. Therefore, in this way, okay, then we normalize all these constant, take into account that in the linearized framework, every constant split in two parts, the Poisson and the thermal creep part. I will indicate with P, the part concerning the Poisson flow, and with T, the part concerning the thermal trip. And the most important parameter is delta, that gives to you the rarefaction regime in which we are working on. And in our case, delta is much greater than 1, because we are in the near continuum. And then if one normalizes this constant on this factor, one can recognize that your original functional J split automatically in three parts, simply grouping the term proportional to k theta square. Theta is in the framework of the BGK is the mean collision time between the two molecules. In the framework, for example, of the Earth sphere is a length scale, let's say. And so the first part of the functional that I indicate with J1 is proportional to k theta square. K, remember, is the adimensional pressure gradient. The second part of the functional J2 is proportional to tau theta square, where tau is the dimensional gradient of temperature. And the last part is a combination, it's the product between the two. The important, but as you can see, all these three functional we derive from the unique initial functional are polynomial of second order of the constant AP, CP, etc., that we want to we want to find the optimal value of this constant in order to minimize our functional. And all these coefficients, C11, C22, can be computed exactly analytically. Practically. As you see, all these coefficients are practically written, can be derived by hand, and they depend only on the rarefaction parameter delta. Of course, they depend on the two coefficients which appear in the Cherciniani boundary condition, alpha t and alpha n. And there are only some terms that I indicate with J1, J2, and J3. And this integral can be defined with this square bracket. The definition of the square bracket is this one. You have to compute the integral of the product between the sum function of the molecular velocity and the linearized Boltzmann collision operator applied to the same combination of the molecular velocity. And this, okay, this is an 8-dimensional calculation, and we did by using the Monte Carlo method, but because we had 4 of these, but in order to test this Monte Carlo method to compute this integral, and let's say the only numerical part inside this kind of a calculation, I found a very old computation made by Wan Chang and Hulenbeck by hand. But let's say the computation of one of these or similar integral took 200 pages. So at that point, I decided, okay, perhaps I can use the Monte Carlo and to check a posteriori that my calculations are enough accurate. But in principle, it's even not necessary to compute this stuff here numerically, but you can do by hand. Also, this part can be done by hand. Okay, this is the expression of the linearized Boltzmann collision operator for the sphere and so on. And then what you can do is to derive these 3 functional, J1, J2, and J3 with respect to the constant, put this derivative to 0, define the optimal value of this constant, put again back this constant inside here, and then you can find the minimum of our function. The coefficients are the same as before, and everything is analytical. Now, since you have seen that your original functional J can be automatically split in 3 parts, the problem is solved. Because grouping now the term proportional to the same scaling factor, you can be able to compute this dimensional factor, which gives to you the flow rate for the Poisson flow, the flow rate for the thermal creep flow, and so on. Simply rescaling this factor and grouping on the 2 sides, on the left-hand side, the right-hand side, the term proportional to the same factor. And then at the end, what you obtain is that the 2 quantity we are interested on, the Poisson mass flow rate, the thermal creep mass flow rate, are exactly the minimum of the 2 functional J1 and J3, and that's it. At this point, since you have everything written analytically, you can perform an asymptotic expansion on this formula and write down the formula that can be proved to describe the rarefaction regime that we want to analyze, and where you see we have introduced this sigma 1, sigma 2, etc., etc. And all these parameters, okay, delta is the rarefaction parameter that we said is much greater than 1. The other sigma factor that you see derive from the previous variational calculation, and also this can be written down analytically. And yes, of course, and then you can compare the solution of the Navier-Stokes equation with this boundary condition that I showed you before, the slip boundary condition, you see, and therefore you can identify these two slip coefficients that you insert in the Navier-Stokes as a boundary condition with the asymptotic solution that you obtain from Boltzmann, starting from Boltzmann. And therefore, for example, in GT, this sigma 1t is the first order slip coefficient that is inserted, that you can use in the boundary condition of the Navier-Stokes. And so you can predict in this way this coefficient that should be inserted in the boundary condition of the Navier-Stokes. Okay, here there is another parameter also further this slip coefficient that can be computed in this framework, this exponent gamma. This exponent gamma is the link between the, if you remember the description of the experimental apparatus that I gave to you at the beginning. So a microchannel set between two reservoirs, and then first a thermal creep flow appear, and then a counter flow given by the Poiseuille flow, and at the end a situation of equilibrium is reached where these two kinds of flow are matched. And in this equilibrium situation, you can write down the direction of the pressure between the two reservoirs and direction of the temperature between these two reservoirs, and they are linked by this exponent gamma that can be also computed by using our variational stuff. Here is a comparison between some experimental result where this slip coefficient, I will show you only the thermal part. An analogous thing can be done also for the Poiseuille part, but here just to give to you. And here, practically, the comparison is done in this way, because in order to extract the accommodation coefficient alpha t and alpha n, that are parameters very important to be extracted from the experiment, because then when one wants to simulate a realistic problem with the Boltzmann equation, should put and use, for example, the Cerciniani-Lampis boundary condition, one should know this accommodation coefficient, the value of alpha t, alpha n, and how to compute this. Therefore, what we did is try to impose the value of these two parameters, sigma 1 and sigma t, close to the experimental result, because then we have this analytical formula. And if we can invert this formula and obtain alpha n and alpha t, which give to you a close match with the experimental result. Here, just to present to you some result that we obtain. The black line are the theoretical prediction by using the variational, and the red point the experiment for different gases. Here is the helium. I will present here the thermal creep mass flow rate again versus the rarefaction parameter. Here is the helium, and then neon, argon, krypton, and xenon. And of course, we were enough happy to have this good accuracy. But the most important thing is that the good accuracy is not only for one parameter computed, for example, in this case, the thermal creep mass flow rate, but also for this gamma exponent that I showed you before. If you then, by using the same accommodation coefficient that you extract from the other computation, you can also recalculate other quantities as gamma, for example, and for the same gas, you see that you can obtain also good accuracy also for this. So just to conclude, Boltzmann wrote also a poem, Beethoven im Himmel, and this poem was managed and translated by Cercignani in Italian. It tells about a journey of Boltzmann, of the soul of Boltzmann to heaven. And there he meets the soul of Beethoven that he loved very much. And Beethoven asked to Boltzmann what he thought about the new pieces that he composed in heaven. And in heaven, Boltzmann said, the beauty is not the same as your previous pieces in your life. And Beethoven said, yes, you are right. Here I have not the right inspiration because, you know, in heaven there is no sorrow. Therefore, it seems that the pain is the most important thing to have this great inspiration. And Boltzmann loved a lot to play piano. And unfortunately, this is the only similarity that I can share with this great scientist. Thank you very much for your attention. Sorry, I was a little bit late, I think.
Okay, good. Any question? Okay.
Thank you, Silvia. Very, very quickly. Well, we could discuss about the pain argument, but that's another talk.
But I do not agree.
That's the next meeting.
That it is the main.
No, very quick question, nothing to do with the pain. Can you handle any Knudsen number in your formalism?
Yes.
So,
but of course, the test function, I have done this when I manage the BGK Boltzmann equation. And of course, in principle, you can do this thing also in the case of the true Boltzmann collision operator for hard sphere, but I plan in the future to try to improve also this part, considering much more realistic interaction potential as the Lennard-Jones and so on. I am not sure that I will be able to write everything by hand, but I want to try. Of course, your test function should be much more complex because you need these exponential terms. The result that I show, in any case, are good between delta equal to 3 until 40, for example. So they are right, even we accurate according to the experiment. I don't want to say right. And so even if your test function is enough simple, like this one, you are able to describe the main part of the transitional region, for example. Then usually in free molecular flow, you have analytical solutions. So, but also, in fact, in the experiment, they could cover with their measurement the same range, because also experimentally it's very hard to be able to measure the right quantities in between the free molecular flow regime and the initial transitional regime. But in principle, yes. But then when you take into account also this exponential, imagine that you have to apply then L, the linearized operator, to this exponential. So you have to be careful with the mathematics, what can you obtain. But if you throw away this exponential, everything is enough simple. You have to...
Other question? Just a very quick curiosity. At a certain point, you mentioned the situation where the collision of the molecules with the wall are more important than the collision among them. So this is a regime where the kinetic theory is not accurate. Maybe it's necessary to introduce some change.
No, it's accurate because in principle, Boltzmann is accurate for everything. But you have to distinguish
Okay.
the kind of which kind of the Boltzmann equation to save, for example, time you can apply. In the situation where you have only where the interaction with the wall are much more important than is the initial part of the transitional region between the free molecular flow regime and the transitional region. And but yes, in this situation, let's say the boundary conditions are much more important than the potential that you use in the Boltzmann collision operator. So it's not so important the kind of potential that you insert in the collisional operator to describe the interaction between the molecule, but it's very important the boundary condition that you associated to the Boltzmann equation, because the scattering with the wall is much more important.
Thanks. Okay, we thank the speaker.
Thank you very much.
Now we have, okay, the last speaker of this section is Antonio Prados.
So thank you, Angelo and Andrea and all organizers for inviting me to this impressive place. I've been here in Tuscany several times in my life, but not in Pisa. So it's nice to be invited here and to do also a little bit of sightseeing if it is possible. So what I'm going to speak about today is beating the natural timescale for relaxation with optimal control. And this is a work that I've been doing in collaboration with some people. My main collaborators in this are from Seville, Carlos Plata, Antonio Patron, and Natalia Ruiz-Pino. So this is the outline of my talk. I'll start with a little overview and motivation of the work, and then I'll move on to the two physical systems that we are going to address today: an uniformly heated granular gas and a system of harmonically confined Brownian particles. And well, we'll finish with some conclusions and perspectives, of course. And I hope this is going to work, but it's stuck. Now it's working. What I'm going to speak about is accelerated connections between given initial and final states. And this kind of stuff was first developed in the quantum framework some years ago. It is known as shortcuts to adiabaticity, STA. And later has been transposed to classical systems, both for Hamiltonian and for Langevin-Fokker-Planck dynamics. And a recent review on the classical framework is on archive right now. So the thing is that the dynamics of the typical system that we're interested in is controlled by some other physical quantities that can be tailored, controlled. These are the control functions in the mathematical framework. And the general idea is to construct protocols, to build protocols for those quantities, for those control functions that make the connection between the initial and the final state faster. Different strategies has been worked out: inverse engineering, counter-adiabatic driving, fast forward. Well, I'm not going to enter into details here. The control functions that I will employ in this talk are basically two: the stiffness of the harmonic trap, in which the system, the Brownian particle is trapped, and the temperature of the environment, the temperature of the thermal bath. The focus of this talk, in fact, it is the second one. And still, I'm going to talk a little bit about engineering the stiffness of the trap. That is the thing that was first done some years ago. In this, for instance, one of the first papers was this Nature Physics. They consider the harmonically confined Brownian particle described by the overdamped Langevin equation. Okay, and the typical noise term with fluctuation dissipation, etc. But the idea was to control the stiffness, to change the stiffness in the controlled way with a certain time-dependent program, and to go from equilibrium at the initial value of the stiffness to a final value of the stiffness, but not letting the system relax for an infinite time with the typical relaxation time of if you do what is called in this context, sometimes the step process, letting the system relax at the final value of the system, and that's all, okay? So we want to beat somehow this relaxation time by making the connection faster, engineering, putting some special protocol for the stiffness, okay? The thing here is that as the PDF of the position is Gaussian for all times, everything is characterized by the variance, so it is quite simple in some way. And what the authors did was to compare their protocol to this step process. That was what I was describing before. I don't know if it is working. It is not working. But this step process, the authors simply put the final value of the stiffness there and let the system relax. Then it relaxes exponentially, basically, with this equilibration time. And this is like the natural time scale for relaxation that I want to beat with my protocol. Well, not my protocol, with their protocol in this case. Okay. The ESC process is consider this equation, the equation for the evolution of the variance. We want to go from equilibrium at the initial time to equilibrium at the final time. So I have some physical boundary conditions. The initial value, the initial equilibrium value of the variance, the final equilibrium value of the variance at the final value of the stiffness, and given initial and final values of the stiffness also to keep equilibrium before and afterwards somehow, although this condition could be relaxed, and we will speak a little bit about that. The thing is that is this accelerated connection possible? Is it possible? Yes. The thing is that you can do what is called sometimes inverse engineering. That is, well, let us put a connection that do the thing. That's the thing, okay? Let us put, for instance, a simple, as the authors did, third order polynomial ansatz for 1 over the variance, because it is the simplest thing to do, and then take the stiffness that does the job from that ansatz, okay? The thing is that, well, one is doing here is simply solving the equation for the stiffness, okay? And well, this works. It has some problems. For instance, if the connecting time is too short, then this term, the term proportional to the derivative of the variance may become too large, and then the stiffness may become negative, that it is not convenient from an experimental point of view, and this hints at the existence of a minimum connection time if you put the restriction that the stiffness must be positive for all times. Okay, but the thing, and this is one of the, I think it is a very clear picture that it is on that paper. This is like the black, or I think it is dark blue, but it seems almost black here. This black curve is the ESE thing that is much faster than the red curve, that it is the free relaxation by simply putting the final value of the stiffness and letting the system relax. The equilibration time for the step, it is about 45 milliseconds, while they got a connection time that is half a millisecond. It is like 100th, the typical relaxation time. And what the authors show is that even doing this kind of very, very fast connection, the system is still equilibrated at longer times. Okay, it remains there. It is not going from that. What for? Well, of course, theoretical interest, but also practical. For instance, in our physics degree courses, they taught us that reversible heat engines have 0 power because the typical cycles have involve an infinite time, but in practice, one has irreversible counterparts of the typical heat engines that with finite time branches. Okay, and if one wants to build theoretically this kind of stuff with harmonical confined particles, for instance, then when one has to do this kind of thing somehow. Okay. These are typical examples, the Stirling cycle with isotherms that are the thing that I've been showing you, this ESE thing with fixed temperature but variable stiffness. But for instance, for the isocores that are the other thing that one has to consider to make a Stirling cycle, one has to fix the stiffness and to consider the variable temperature. And over the adiabats for other cycles like Carnots or Ottos, then we have to know what is an adiabat in this context, etc. Okay. So is it possible to engineer the thermal environment? Because one thinks, to engineer, to change the temperature, one has to actually change the temperature of the bath. The thing is that this difficulty, one can make a trick somehow to change the temperature in a wise way, considering a charged colloidal particle and adding a random electrical force. Okay, and then this random electrical force is over time scale that one is interested into, typically in the overdamped limit, it is basically white noise. And then the variance of this random electric force is being added to the variance of the heat bath, to the temperature of the heat bath, and then one may heat in an effective way the particle. The particle is feeling a white noise force that has a variance that has 2 contributions, and one can go from room temperature to thousands of kelvins in this way. And this is what, in fact, done in these papers several years ago, and they constructed a quasi-static adiabatic in the sense of zero heat processes, in which they showed that the thing was that to put T squared over kappa equal constant to construct this quasi-static adiabatic thing. If one wants to build a finite time adiabatic branch, then the second principle tells you that T squared over kappa is not constant, but it is increasing because of the entropy production. And also it tells you that there is a minimum time for an adiabatic connection in the sense of zero average heat. And this is one graph from one of our papers about two years ago, in which it is plotted. What is plotted is the minimum connection time over the adiabatic thing as a function of the temperature, and it is observed that you have a minimum time from the adiabatic connection. That in fact it is when you do nothing, the final temperature and the initial temperature are equal. This is undimensionless temperature in terms of the initial temperature. So one, it is the initial temperature. And then you have this kind of plot, typical plot. So somehow here, there appears the idea of a speed limit of minimum connection time, that it is different from zero. In the case of the harmonically confined particle, changing the temperature, the stiffness in principle, you could do that theoretically as fast as you want. Okay. And in other contexts, first with Markovian dynamics in this paper, later this was generalized for general dynamics. it has been shown that there is some kind of natural time scale for relaxation in classical systems with these kind of ideas that were originated in information geometry theory, okay, this Fisher information, and that enters here in what is called the thermodynamic length and the information cost, or the divergence of the thermodynamic length. And it has been shown that the connection time must verify this inequality, that it is a simple consequence of the Cauchy-Schwarz inequality. It is not difficult to show that. Okay, it is a couple of lines. It will be finding in these two papers. So with entropy production, for instance, for me it is not clear. I mean, in linear response, it has been connected by Crookes some years ago. There is a connection between this kind of quantities and the irreversible work somehow, but outside linear response theory, to the best of my knowledge, it's not clear. The physical interpretation of this quantity, for instance, of the cost. In fact, it is something that I'm interested in, but I don't have a clear interpretation for that quantity in general. Some questions that I want to address in my talk. Naturally, there appear some optimization problems, the minimization, for instance, of the cost, either the irreversible work or this C, okay? The connection time, other figures of merit. The control functions that I'm going to employ are typically bounded, in the sense that they are non-negative, or they have some practical bounds, okay? They may have jumps. Even in the step process, that is the simplest thing, they have jumps. So they are piecewise continuous. And then the natural thing is not to address this kind of optimization problem in terms of variational principles, like Euler-Lagrange equations, etc., but in terms of the optimal control theory, Pontryagin's maximum principle, for instance. And, well, of course, also from a physical point of view, all I have spoken till now is about connecting equilibrium states, but you can also ask about what about connecting non-equilibrium states, for instance, non-equilibrium steady states. In this talk, I'm going to address I'm going to term the thermal brachistochrone, the fastest connection, by only controlling the temperature, or the quantity that plays the role of the temperature. For instance, in the granular thing, it is the intensity of the thermostat, okay? I'm interested in comparing the minimum time over the brachistochrone with the relaxation time in the step process, and also with this kind of bounds from the information geometry. And I'm going to do that in two different systems, the uniformly heated granular gas, and also in a system of harmonically confined Brownian particles. Okay? I'm more or less fine. So let's start with the uniformly heated granular gas. I'm going to try to skip the details and to give the basics of what we have done during the last years, and the details you can find them in the papers, okay? Or you can ask me later afterwards. In the granular gas, what I've used is the simplest model for a granular gas, hard spheres, smooth, okay? No friction, and inelastic collisions, okay? Instead of having an elastic collision, then what I'm going to have is that the tangential velocity is conserved, but the normal velocity is shrunk by a certain factor that I call alpha, okay? Alpha equal to 1 is the elastic case, alpha equal to 0 is the completely inelastic case in which the two particles continue together after the collision, and in between you have all the possibilities. And the typical thing that somehow connects with this conference is that what is used here is the inelastic Boltzmann equation. one thing that makes the problem different from a mathematical point of view is that the PDF is non-Gaussian, even for the steady state, okay? And then one has to use typically to employ some kind of approximation scheme to solve the Boltzmann equation. And what I'm doing here, that's the typical thing that has been done for, I would say, 20 years. It is to employ the first zoning approximation that works quite well. It's not perfect, but works quite well in most situations. And in this approximation, then the solution to the Boltzmann equation is characterized by two parameters: the granular temperature, that is basically the kinetic energy, okay, and the excess kurtosis A2, that it is a more or less complicated combination of the fourth and the second moment. But the important thing to me is that measures variations from the Gaussian thing. It is equal to 0 in the Gaussian case, 0 in the non-Gaussian case. Okay, and it is enough for most things. Okay? For some very difficult stuff, you have to improve this approximation by considering further cumulant.
Yeah, one of the things he's going to mention is the paper that we published together.
And well, I have some dynamical equations for T and A2 that I'm not going to write here, only that the time derivative of the temperature is certain function F1, and the time derivative of this dimensionless A2 that is equal to 1 in the steady state because of the non-dimensionalization is equal to some function F2. The important thing to me is that both functions are linear in this chi, in this control that I'm going to address. And well, I have already said that. And my idea is, I insist on this, it is to drive the system from an initial value of the temperature, initial value of chi, to a final value of the temperature with a final value of chi. A2 is equal to 1 in the two states because it is independent of chi. Okay, this is a very specific thing here. And it's also where is the guy from the staff, because maybe I don't know. I think that every time they touch, yeah, it's changed. Okay, I know that. I can't change the slide because I think that you have to somehow. Yeah, it's there.
Yes, but what's that?
Okay.
Okay.
So, sorry for that. So first, is it possible here to do the connection? Well, the first thing to do typically is inverse engineering. You consider here you have a problem that it seems in principle to be less clear cut than the first one, because the one with the harmonically confined particle, because there you had one control and one variable, so everything seemed clear. But here you have one control and two variables. Well, I can control that. The answer is yes, of course. You only have to increase the number of parameters. There you have the third order parameter, the minimal thing. Here it is a fourth order parameter, but it works. Okay, so you can put some connection here. It is because of the mathematical structure of the problem. The simplest thing is to consider a polynomial connection for the square root of the temperature. Then you put there some connections with different connection times. This is the shortest, this is the largest, and then the inverse engineering thing that it is solving for chi, basically. You get the k that does the job, that it is okay, this kind of thing. And you notice here a problem, it is the same problem as before, that in a certain time window, this chi becomes negative for a very short connection time. And this is a problem because this chi is the variance of the thermostat that cannot be negative. So this is hinting at the existence of a minimum connection time. And indeed, you can increase the degree of the polynomial and you continue to see this if you decrease the connection time. Okay. And in fact, if you do the optimal control thing, we will show that in fact there is a non-zero optimal connecting time. And the mathematical structure of the optimal control problem in this case is quite simple. You have to minimize this. This F0 is simply equal to 1. Okay. You have a physical constraint that this chi must be positive. And you write Pontryagin maximum principle that it is quite simple. Okay. If you have studied, all of us have studied classical mechanics in our degree, this is quite, it is not typically taught at in the degree of physics, but it is, it gives you some, you recall some things here because you first construct like a Hamiltonian. It is not exactly the Hamiltonian of classical mechanics, but it is like a combination of these F1, F2 that are the right-hand side of the dynamical equations with these sides that are the moments, this F0 that it is a constant, but in the end it is going to -1. So it is like the changing from the Lagrangian to the Hamiltonian thing. You construct the canonical system from this Pontryagin Hamiltonian. And the point is that in order to look for the optimal solution, what you have to look is for the maximum of that Hamiltonian, that Pontryagin Hamiltonian, as a function of this chi. And the thing is, and this seems to be like a very general part, a very general feature of optimization problems with the temperature or temperature-like quantities, that these functions, F1, F2, all functions are linear in this chi. So you don't have a maximum for these functions, and then if you don't have a maximum inside, you cannot make derivative of the Hamiltonian with respect to chi equal to 0, because chi disappears when you take the derivative. Then you have this kind of bang-bang problems. You have the maximum at the boundaries. Depending on the sign of the derivative, you can have the maximum here, or you can have the maximum here, but you have the maximum and the boundary. And this is the bang-bang thing. You have to put there the maximum, either the maximum or the minimum value of the control function. Okay. So I'm going to show you some figures, some graphs for the granular thing. This is like the initial state that in dimensionless variables it is 1, 1, and I'm going to go to this state here. So I have to do a 2-step process, a 2-bang-bang process. First, I have to hit the system with the maximum possible value of chi, and afterwards let the system relax with the minimum possible value of chi that is equal to 0. Okay, so this is like heating with the maximum temperature that I have taken equal to infinity. Okay, I have taken the limit for the sake of simplicity, and afterwards the system freely cools until it gets the final state. If the first temperature, the first chi max goes to infinity, then this is instantaneous, and the connection time is only the cooling time over the second part of the bang. Okay. This is for temperatures larger than 1, but the thing for temperatures smaller than 1 is basically the same, but the order of the bangs is reversed. If you want to go to a temperature that it is smaller than 1, it is smaller than the initial one, then you first have to cool, and afterwards you have to heat the system in the strongest way you have. Okay. It is impossible to connect the two states if you reverse the bands. If I first cool and afterwards heat, it can be shown that you cannot get to a temperature larger than 1. So this is the solution of the problem in principle. Okay. You can ask why only 2 banks? You can make 4 banks, for instance. You can make, if you want to go there, you can go here, then afterwards heat and make more complicated things. the point is that you can show that lasts a longer time, and this is shown in another paper, okay? Because here the system is not linear. If the system were linear, one would invoke some properties of the control of optimal control theory that tells you that the two-bank thing is the optimal one, but here you have a non-linear problem, so you have to prove that, okay? What is the comparison between this connection time with the typical relaxation times? Well, this is the connection time for heating for temperatures larger than 1 as a function of this TF. It is less than 1/4. And for instance, this kind of a speed limit, it is over 1/2 for the whole range. Okay, so it is quite shorter. I have also compared here the connection, the optimal connecting time with the relaxation time, but for the step process, well, like the experimental relaxation time somehow. And what you get here is that this is the inverse thing. So it is like the acceleration factor that you get in this kind of stuff, and it is over 20 over the whole range of temperatures. Well, everything is theoretical up to now. So one may ask, well, this is approximate. You are only working with 2 parameters, the temperature and the kurtosis, and is this really working in simulations? Because you can solve numerically the Boltzmann equation, and then afterwards see if this kind of protocol that you are employing is really doing the thing and is really being stationary after you put the system there at the final time, or it is going to go to some excursion because it is not, you have forgotten higher order cumulants. And the thing is that in fact it works quite well. Okay, this is a graph in which the green line is the temperature. This is like negative times in which the system is in the non-equilibrium steady state corresponding to Ki, okay? And this is this straight line, it is like the final state in which you have put Kf and you put there and it is at rest, okay? And the interesting thing is in this small time window in which the temperature is changing, okay? And it is going, this is the heating, that it is instantaneous, and then afterward it is being cooled. Here there is some slight fluctuations, but they are so small that over the scale of the figure, it seems that it is a perfect straight line, but it is, you can see some structure if you look at it. Of course, there are more fluctuations in A2, okay? It is much more delicate quantity, but it is stationary before and it is stationary afterwards. Okay, the system is not doing anything. Okay, and this is the comparison between the times that you get in the simulations and the time that you get with the theory. It is quite good taking into account that it is a first-running approximation for the Boltzmann equation. You are neglecting third and higher order cumulants. Everything that I've shown you up to now, it is for infinite heating power. This Chi max was equal to infinity, and then the first heating of the second heating, depending of you were cooling or heating, is instantaneous. But if you have limited heating power, the thing is that you, in the general case, you cannot do something analytical. It is much more difficult, but you can do things in the linear response regime. Okay, so this is what we did quite recently, and we showed that, well, basically it is the same. You have this kind of two-band thing, heating, cooling. If you want to go to a temperature that it is larger than the initial one, heating first, cooling afterwards, this is A2. And this is the same for cooling, first cooling, then afterwards heating. And you can, well, check the validity of the linear response approximation, that it is it extends to certain regions in parameter space where you don't expect it to work well, but it works better than expected somehow. Some summary, a brief summary of what we have done up to now in this system. Y1 bang, because the linearity in the control chi of these evolution equations for the temperature and A2. Why not only one bang? From an intuitive point of view, it is like you need two bangs because you have two things to have the temperature and A2. And then if you cut the protocol here, the problem is that A2 is not going to be on the right value. Okay, so somehow you have to overshoot the right value for the temperature in order to get to the steady state simultaneously for both T and A2, because that's what you want to connect the two, not equilibrium, these two non-equilibrium steady states. Okay. So somehow the second band meant there or introduced by the first, but it is not as simple as that. You have to overshoot really the first value. And why not more than two? Because basically they involve longer times. This is like the initial state, the final state. The bang thing is doing like this. You can think that, well, I can go here, afterwards do this line, afterwards go upside, and then to the right. You can show that this is longer than the two things. Okay. Of course, if you have other problems in which you have to employ higher order Sonnino approximations with 3-4 parameters, then you should have additional bands, not only 2, but 3, 4, how many you need. The same thing basically, but for harmonically confined Brownian particles. This is in this paper. Here, the starting point is not the Boltzmann equation, but the Langevin or the Fokker-Planck equation. The point is that although I have a d-dimensional problem, not a one particle in one dimension, as in the Nature Physics paper that I showed you in the introduction, I have a d-dimensional problem. The PDF is still Gaussian for all times, and I can go to normal modes and get a system of uncoupled equations for the variances. Okay, so it is like a system. It seems not very interesting at first. No, it is when you have uncoupled equations. This is going to be quite easy, but there are some surprises, at least for us. You go to dimensionless variables. You get the dynamical equations for the variances. Here the control function is this temperature that I'm going. If I would like to, it would be nice to do this experimentally. If one wants to control the temperature in experiment, remember you don't hit actually the bath, but what you use is a charged particle, and you put this additional random electric field, and in order to increase the temperature of the bath in an effective way. Okay, that is much easier. And what I want to connect is the initial equilibrium state and the final equilibrium state. In this case, these are two equilibrium states corresponding to different values of the temperature. One in the initial state in my dimensionless variables, TF, the final state, and the stiffnesses are going to be constant. Okay, it's like an isoporic process here. No work. The mathematical structure is quite similar. I'm going to minimize the connection time. I have a physical constraint that the temperature is constrained by the room temperature, Tmin, Tmax, thousands of kelvins, but there are something there. Okay, I construct the Hamiltonian. I have here d terms instead of 2, but well, it's similar. I construct the canonical system. I look for the maximum of pi as a function of t and get the optimal temperature, the optimal program. But as all these functions, these fi are all of them are linear in the temperature, then again I have a bang-bang process. And here I have a theorem because everything is linear that tells me that the bang-bang with the minimal number of bangs, it is the thing that gives me the minimum time. Okay, so that's an advantage. So the number of bangs is equal to number of variables. If I want to heat, it can be shown that I have first to heat, afterwards cool, heat, cool, heat, cool. And if I want to go to a value of the temperature that is smaller than my initial value, then I first have to cool, afterwards heat, etc. Okay, somehow like the order is that the first one is in the right direction. Okay, to remember that. If I make, as before, an infinite heating power assumption that basically the upper bound is irrelevant, then this kind of processes with the maximum value of the temperature are going to last 0 time, and this simplifies the thing. So well, let's do it for the sake of doing analytical predictions. Okay. And the thing is that, well, I'm going to focus on final temperatures larger than 1. Okay. D equal to 1 is trivial. The best thing is instantaneous. You put infinite temperature, and when the temperature, when the variance of your Brownian particle hits the value, the final value that you want, you cut the infinite temperature protocol and you put the correct temperature, and it is going to be there. So you can, this is in agreement with what was done in these Nature Physics papers some years ago, that you don't have a physical restriction for the minimum time in 1 dimension. Okay, but if you put more dimensions, then even if you have an infinite heating power, then you are going to have a finite minimum time, because you have to combine heating bands that are instantaneous with cooling bands at the minimum temperature that are not instantaneous. Even if you put that the minimum temperature is 0, okay, you cannot go to minus infinity because the temperature is positive here. Okay, if you could go to minus infinity, then you would have perfect symmetry between heating and cooling. But the thing is that the lower bound is physical, it is not practical. Okay, so d equal to 2 takes a longer time, d equal to 3 a longer time. This is not very surprising. Okay, this is for k. Well, I have made things dimensionless in the stiffness with the first k. The second k is double. The third k is triple, whatever. Well, that is not. But the thing is that you have this graph, and it seems it is the same as the previous one, but this is almost spherically symmetric. Okay, the difference between the stiffnesses is very, very small. Of course, if I put everything equal to 1, then it can be mapped exactly onto the one-dimensional thing, and it is going to be the fastest thing. The optimal thing is to go with an instantaneous band at infinite temperature. But if you have the slightest change from spherical symmetry, then you are going to have that d equal to 2 lasts longer than 1, that d equal to 3 lasts longer than 2. And this is because you have to spend some time cooling. You have 2 variables. The difference may be as slight as you want, but you are not going to address to reach perfectly the target point. Okay, and then you have to do the 2-band thing, and the second band is not going to be very, very short. It's going to have a minimum time. Okay, so it is quite curious that you have these finite jumps in the minimum connection time. And you can do that for analytically for 0, 1, 0 for dimension 1, 1/2 for dimension 2, 1 for dimension 3. This is not so easy. After that, this is analytical, this is analytical, this is numerical, okay? Because you have to solve some polynomial and then you don't have an analytical solution for that degree. Well, 5, it makes sense. Yes, you can have 2 Brownian particles, no, in 2 different traps. And from an experimental point of view, you are not going to have exactly the same variance. You are going to have some error. And then if you're going to have some error, some difference in the variance, you will have this kind of thing. I hope. No? So conclusions and perspectives. Okay, I'm more or less on time, I think. Well, I have studied this thermal brachistochrome and shown that it is bang-bang under very general conditions. The reason is that the temperature, the control function, or the intensity of the thermostat enters linearly the evolution equations. The number of banks is equal to the number of relevant variables, 2 in the granular gas case. Here, the dimension of the system, basically. This entails discontinuities in this minimum connecting time that we would like to understand better. It can be shown that in general, this kind of optimal connection is much faster than both the typical relaxation time and these geometric speed limits. Perspectives for the future. Well, I would like to understand better in connection to also what with Angelo asked before, the role of these thermodynamic geometric cost things that I don't understand very well right now. The possibility of new features that may arise in the underdamped limit. The underdamped limit is typically much harder. It is not so clear-cut. And also in connection with this kind of discontinuities in the connection time, what about imperfect targets? So from an experimental point of view, it is almost the same to be at the exact point, at a point so close to the exact point that it is inside the fluctuations somehow. So does this kind of discontinuities survive if one puts some experimental error on the target point? Disappears? Depends on the precision that you have. I don't know. Okay. So thank you, of course. Questions, comments are welcome. I also want to acknowledge the funding from the Spanish government, and this is the team basically that Carlos Plata, that is now a Marie Curie Fellow, and 2 PhD students, Antonio Patron, who is in his 3rd year, so probably looking for postdoc soon. So if you have one are interested in this kind of stuff, you can contact him. And Natalia, who is starting right now, and is I don't know if she's going to work in this kind of thing or change subject, but well, also very student. So thank you.
Question?
Hi, thank you for your nice presentation. So, do you think such accelerating protocols, I mean, exist for general long-range interacting systems? Because there the system can be, I mean, stuck on quasi-stationary states.
Oh. That's a tough question. I haven't thought of long range. I don't know. It would be interesting to look at that, but to the best of my knowledge, this has not been addressed. The problem of trying to look for this kind of stuff in a long-range interacting system. I don't know. I'm not aware of that. It is interesting for sure, but I'm not aware.
Okay.
In principle, I don't. I don't see a fundamental problem in doing this kind of thing, but at least inverse engineering and this kind of simple connections, optimal control, and this kind of configuring thing, this may be harder, but principle inverse engineering, I think that it should work. It should work. Okay.
Okay, thank you.
A simpler version of the previous question.
Okay.
You consider these Brownian particles which are independent, right? So they don't interact with each other; they just interact with the bath.
Yeah. They only interact
So
with the bath.
question
They
is,
are far enough, or they're not. Okay.
Exactly. So, did you ever study? Do you think it's relevant to study interaction between particles, or is just and there is some motivation for that? For example, in these colloid experiments, or just academic?
If the interaction is, if the interaction is linear somehow, then this is included in what I have done, because it is
yes,
because you go to normal modes, no?
Yeah, but the temperature, the bath. No, but the bath feels, each normal mode feels different. The temperature, the fluctuations are just one, no? Just the bath fluctuation. So each normal mode will feel a different strength of.
No, but the temperature is the same for
Yeah, that's what I mean.
Yeah. And that the stiffness in principle here can be different. When I write here these equations, this is like the stiffness corresponding to the.
Yeah, but the noise term will have a coefficient in front which will depend on the mode.
What?
When you go to normal modes.
No, but it is when I go, this is already normal modes, and it is the same because the Jacobian is 1.
Yeah, I understand, but
that in the original variables you have this thing, but when you go to normal modes, it is still one thing.
No,
This is one thing that in fact, when we started doing that, we didn't have that kind of thing clear, but it works. You go to normal modes and you still have only one thing. Other thing is that if you have a nonlinear coupling between and it is much harder. But in principle, if the coupling is linear, this should work for normal modes.
But is there some physical system that where this interaction could be important for optimal protocols, or you think is more or less?
I don't know. Right now, for instance, there are an experimental group in Granada that it is trying to do this kind of connection with two electrical plates, running particle in a two-dimensional setup. Okay. But in principle, that kind of experimental setup enters in our framework. It is difficult to know if you can. Okay. But in principle, what I would say is that provided that the interaction is linear and everything fits in the model, in principle, I should say that it will correspond to what I'm showing here, but we can discuss about that later. Okay.
Thank you for the talk. My question is, your protocol is different from the one that you showed at the very beginning of the talk.
Inverse engineering thing.
Yes, but my question is, when you use a finite number of, for example, let's take the Brownian particles. When you use a finite number of particles, is there a difference if you use one or the other in the statistics, that you obtain about some quantities in the final distribution? If you have to measure, for example, how good is your final distribution, is better to, have you tried to compare the two protocols?
compare the two protocols in what sense you mean?
For example, if you
how,
have
how would they are in targeting the final
exactly, if you have 1,000 particle and you do your protocol, or you do the other one, or any other protocol, the final distribution will be better. I mean, it's only a question, not maybe you do. For finite sides, I mean, if you have finite.
In principle, I should say that I don't see a fundamental reason to have problems for one protocol or the other. I would say that in principle they should be more or less comparable. I have not done the test.
Okay. Yeah.
You should, some sense to measure the distributions and to put some tests that are something that quantifies what you are saying, more or less in a qualitative way. But in principle, I don't see a reason to think that, for instance, this you can ask also the same question here. No, it is is this better or it is worse than the other protocol?
Yeah, of course.
Yeah. But in principle, I should say that they should be, from a statistical point of view, almost the same. I don't see any reason to have a difference. And you may have surprises there. I don't know. But in principle, I don't
only another short question. If because usually at the very beginning you mentioned Jarzynski as a co-author or something like that.
Well, of this review.
Yes.
Okay.
My question is, if the trap, for example, is moving, there's maybe some. It's an unusual example for Jarzynski. And in that case, usually there's the problem about the number of for the statistics. So it was for maybe
you can also for sure look at things when you are moving the trap, not the center of the trap, not the stiffness, of course. But we haven't done that because well, in principle, the kind of problem is tough enough somehow with a fixed center. But of course, you could do that. But I don't have. I haven't done that. Other problems in optimization of work and other kind of things. They have done things with moving center. But in this kind of context, I don't think so.
Okay, thank you.
It would be interesting.
Thank you very much.
Sure also. Okay. Andrea.
Yes, thanks for the very nice talk. I was wondering about, I mean, in the last example with the multidimensional harmonic potential, you get in the end the results that the dimensionality is important for the. So the dimensionality of the evolution problem changes for instance, the optimal time.
Yeah, dramatic.
Then I was wondering, in the first example with the granular gas, you decide to represent the gas, the distribution with just two parameters.
Yeah.
That's your decision. Right. In principle, the dimensionality could be much larger. But then you get a good comparison with the Monte Carlo.
Yeah. This is somehow connected with the final question that was I doing here. No, what about imperfect targets? No, somehow in the granular thing, I had an imperfect target.
Okay, you're sure.
And then I get an approximate answer that it is not the exact answer, because in principle the exact answer would have infinite bands or something like that, because you have to match all the cumulants. So if you go, I think that the question that you have what about A3? If I put A3, I have 3 bands, and so how does it compare one thing with the other thing? I have not done that. But what I guess is that we would have also this kind of change of time by a finite factor, and then you have somehow to decide what is best for you, to have a better fit for the final distribution or a worse fit for final distribution, but with a shorter time. It is enough because your precision is that, and then that kind of fluctuations that you get are, well, Is that good for you, or you are seeing some excursions that are too large and then you want to have
so
more...
that could explain also the paradox with the slightly different stiffnesses, no? Where seems that you need much time, but probably because you are asking too much precision for. I mean, you can.
Why we're interested in saying, well, if I don't have, for instance, one point as a target, but I have a small box, okay, what is the minimum time to go to the small box? And it is
to be much faster.
Could be much faster. I don't know. Is there going? Will there be this kind of discontinuity, or will this appear in some limit? Because if we go to epsilon equal to 0, we have the discontinuity, but it appears. How does this discontinuity appear or disappears?
Thanks.
Question? Okay, so we thank all the speakers of the.
Hello. So we have plenty of time, but still, I think it's healthier if you stick to the agenda. And the agenda tells me that the next speaker is Maria Groppi, which we are very pleased to welcome here. And there is a change in the sense that the last speaker of the session, Thorsten Pöschel, is unfortunately got COVID, so he won't be delivering the talk. So we have plenty of time at the end. At 5 p.m. we will be done with the talk by Bruce. Having said this, I would say the stage is yours, Maria.
Okay, good afternoon. First of all, I would like to thank the organizer for this kind invitation. It's really a pleasure for me, a great honor to be here. And I would like to speak about a new mixed kinetic model, which mix the properties of the Boltzmann equation with the BGK features for gas mixture. This is a joint work with many collaborators, but the main one are the people which are in my small group of kinetic theory in Parma, and Marzia Bisi, George Martalò, and a new PhD student, which is Enrico Lucchin. Just some words about some motivation introduction for this work. The kinetic modeling of gas mixture plays an important role in many applications. A typical field of application of a kinetic model is, for instance, the problems of atmospheric re-entry. And in many applications, we have to deal with the mixture. For instance, we can think about the most simple gas, the air, which is essentially a mixture of oxygen and nitrogen. And one of the main advantages of the kinetic equation is the fact that we can derive from the kinetic model in using asymptotic expansion and in the asymptotic limit when a proper Knudsen number tends to 0, hydrodynamic equation, mainly Euler and Navier-Stokes equation, and we can derive this equation consistently from the kinetic level. In this work, I would like to speak about two things. The first one is a BGK type model that we proposed in 2018 with Bobilev, with Giampiero Spiga. I think that is the last work that Giampiero wrote. And Giampiero was the founder of our group in Parma, and he suddenly passed away last January, but he always lives in our memory. In this BGK type model, we try to define a BGK for mixture in which we mimic the structure of the Boltzmann equation. So the Boltzmann collision operator share with the BGK collision operator some important characteristics. In the second part of the talk, we go behind this BGK and we try to combine the positive feature of the Boltzmann description with the ones of the BGK model. And so we propose a model in which the Boltzmann operator describes the intra-species collision. It means the collision between a particle of the same constituent. And the BGK operator describes instead the interspecies collision. The motivation for this new model is the fact that we aim at preserving, wherever possible, the detailed description of the interaction provided by the Boltzmann equation. But at the same time, we would like to have the more simple, manageable numerical treatment of the kinetic BGK model for mixture. The study of BGK models for mixture is a quite active research field, starting from the first paper of McCormack in 1973, because it's not unique the way in which we can define a BGK model for a mixture. We have only one BGK for a single gas, but we can construct many BGK for mixture. And the extension from a single gas to a mixture is not a trivial passage, because there are some drawbacks that can arise. For instance, it is difficult to prove the positivity of the macroscopic fields, especially the temperature, in the BGK model. In this list, you can see you can see some paper about the BGK model for inert mixtures. The red one is the first mathematically rigorous paper written in about the BGK model for mixture. It is due to Andrea and Pertam, and it appears in Journal Statistical Physics in 2002. More recently, there are some other authors working on this subject. For instance, there are a group in Würzburg with Klingenberg, and also Gabriela Pupp is involved in these researches, and also Auk and Murillo that has published a couple of papers about BGK model for mixture, inert mixture. But we can have also extension of BGK model for inert mixture to reactive mixtures. I worked with Giampiero in 2004 about this subject. We consider a simple reaction between monatomic gases. And later we constructed different BGK with Marziabisi, again for reactive mixture. And also Kremer and co-authors works on this field in the beginning of the century. Another field of application of BGK is with reference to polyatomic gases, because also polyatomic gases are useful in the application. And there is a list of some recent papers about polyatomic gases. Our BGK model that we call BBGSP, taking the initial letters of the authors, start from the structure of the Boltzmann equation for an inert mixture. So we consider a mixture of capital N species, and we have the Boltzmann equation that for the evolution of the distribution function Fi of the I component of the mixture as the usual form, with the streaming operator in the left-hand side. And on the right, we have the collision operator, which is a sum of B-species Boltzmann collision integrals. These Boltzmann collision integrals, Qij, are defined in terms of collision kernels Gij, which depends on reduced masses and on intermolecular potentials, and has the classical structure that we can recognize also from the Boltzmann equation for a single gas. Our BGK start from this structure and want to preserve, in particular, the structure of the Boltzmann collision operator. So, contrary to the, for instance, the BGK proposed by Andrea and Pertam, the collision operator is a sum of B-species BGK operators, this Q tilde in red. So we have for the collision between particle of species I and particle of species J, a relaxation term which depends on parameters nu ij, which are the collision frequencies, density ni, and this attractor capital M ij. The attractor capital M ij is a Maxwellian, but it depends on auxiliary parameters. Is an auxiliary Maxwellian depending on auxiliary parameters, which are these T, capital Tij, and bold Uij. These are not the moments of the distribution function Fi, but we have to fix this parameter, assuming some important feature that we want to reproduce by our BGK. So in this description, we have 5n² free parameters, which are the collision frequency Uij, the auxiliary velocity fields Uij, and the auxiliary temperature Tij. And we have, in principle, at the beginning, only the conservation law, which are n+4 conservation laws. So we need some additional assumption in order to define in a unique way the auxiliary parameter that define our BGK. The first assumption, quite reasonable, is that we assume that collision between identical particles are described by the usual BGK model. And it means that for the auxiliary parameter with the index II, we have the true fields, so the true moment of the distribution function. Then the key assumption is that we impose that each bispecies operator Q tilde ij, the BGK operator, prescribe the same exchange rate by collision, the B species exchange rates of the corresponding Boltzmann integral operator. It means that if we take the moments of the B species BGK operator Q tilde ij, and we take moment of the Boltzmann collision operator Qij versus velocity and kinetic energy, we have the same values. Here, the square bracket, the bracket means the usual scalar product. This computation, the computation of moments of the BGK operator is simple, and we obtain the left-hand side in the last formula of this slide. The computation of the moment of the Boltzmann integrals instead involve computation of integral of this kind, and they depend on this Gij1, which is a angle integrated collision frequency, angle integrated cross section and collision kernel. This G1 is not cannot be explicitly computed, but if we have Maxwell molecules, you can do this computation, because the collision kernel in this case is independent on the modulus of Y, and so this quantity is a constant. And we call this constant lambda ij, which is the parameter that have inside the trace of the intermolecular potential. But if we have general intermolecular potential, we cannot compute exactly this integral, but we can do an approximation. We can take, we can approximate the value of this function by taking the value of the argument in some typical points. For instance, we can take the value in the point zeta ij, which are essentially an average of the relative velocity. And so taking, for instance, for zeta ij, this value, we compute, we choose to express zeta ij using this mean, and consequently we can have, in any case, this parameter lambda ij as the value of Gij1 in zeta ij. So we can, in any case, in both cases, we can get explicit expression for the exchange rates of the B species Boltzmann integrals. In the case of Maxwell molecules, these expressions are exact. For general intermolecular potential, we have an approximation. Taking this expression for the moment, we can finally obtain the expression of the auxiliary parameters in terms of the actual field. Essentially, we have that the velocity, the auxiliary velocity Uij are a combination of the actual velocity Ui and Uj of the component I and J respectively. and the temperature, the auxiliary temperature Tij are a combination of Ti, Tj, and of the difference Ui minus J to the square. And the coefficient of these combinations are expressed in terms of the collision frequency, nu ij, this parameter lambda ij, which have, we remind us the intermolecular potential that we have in our model. And then we have this definition for A, B, and gamma ij. This BGK we prove in this paper of 2018, which is we prove that is a consistent model. Consistency in the consistency properties, we means that we can prove the exact fulfillment of the conservation laws. So this BGK conserve the mass of each component, the global velocity, and the global energy. And in addition, it is a good BGK in the sense that it preserves the positivity of the solution Fi and also of the temperature Ti, which is one of the drawbacks that we can face with a not good choice of the parameter of the BGK. The only assumption that ensure these properties is this assumption on the collision frequency nu ij, which must be greater than 1/2 lambda ij and j. This is a quite reasonable assumption, and it is important to stress that the same condition was found by Andreas and Pertam for their BGK in 2002. And this is quite also there is also physical motivation for this choice, so is a good is a natural condition in some sense. One of the advantage of this description with this choice to take a sum of BGK operator Qij tilde, one of the main advantages of this choice is the fact that we can, with this rich collision operator, we can investigate different collision dominated regime. And so we can obtain different hydrodynamic equation depending on the regime we are considering. The first regime that we investigated was the regime in which all collisions are dominant. And so a suitable adimensionalization, suitable scaling of the equation leads to a adimensional Boltzmann equation where we have the factor 1/epsilon, where epsilon is the Knudsen number, in front of the whole BGK collision operator. Another regime that it is possible to investigate thanks to the structure of this BGK is the regime, for instance, in which only the intra-species collision, namely the collision between particles of the same component of the mixture, are dominant in the evolution. This case was already considered by Galki in 1994. He called epsilon mixture the mixture in which we have this such a phenomenon. In this case, a suitable scaling leads to the appearance of the factor 1/epsilon only in front of the dominant operator, which is the operator that involves the collision of one species with itself. Starting from this adimensional Boltzmann BGK equation, we obtain Euler and Navier-Stokes equation by means of a Chapman-Escott expansion. And in the two different regimes, we obtain two different sets of hydrodynamic equation, because in each regime we have different hydrodynamic variable since we have different dominant operator. In the first regime, we have that the dominant operator as collision invariant, and so we have that these are the hydrodynamic variable. We have the species density of each species, the global velocity U, and the temperature T. While, yes? In this dominance scenario, yes, in the first one, the global equilibrium is the Maxwellian with a global temperature and a global velocity. In the second scenario, the equilibria are the Maxwellian of each species. So we have a velocity of each species and temperature of species. Yes, if you put equal to 0, the second, the right-hand side, we obtain that the only solution that make this right-hand side vanishes are Maxwellian with global temperature and global velocity of the mixture. While in the second scenario, the dominant operator is the QII, so we have a sort of separation between the different components in fact. And so these are the hydrodynamic variables in this second case. And this leads, as we can see in a minute, to, in one case, to the classical equation, for instance, Euler equation. In the second case, we have this multi-temperature and multi-velocity Euler equation because we have an equation for each of the fields of the species I. To obtain the macroscopic equation at Euler and Navier-Stokes, we apply the Chapman-X procedure. So we expand the distribution function up to the first order. And in the same way, we expand the actual and the auxiliary macroscopic fields. Since the hydrodynamic variables are not expanded in the Chapman-X procedure, we have some constraint that arise from this condition. And so we have that the first order correction to the number density are 0, but also the first order global velocity and first order global temperature are 0. At the 0 order approximation, we obtain that the solution that make the right-hand side, the dominant operator, which is the right-hand side, vanishes, are the Maxwellian with the common temperature T and the common velocity U. And the leading order auxiliary parameter, which appear in the auxiliary Maxwellian, the active Maxwellian, are in this case provided by these hydrodynamic quantities. And this tell us that at the leading order, in this case, we have the classical Euler equation for number density, velocity of the mixture, and temperature of the mixture. For the Navier-Stokes equation, we have a set of equations for number density, global velocity, and global temperature, and we are able to compute the first order correction, so the diffusion velocity UI1, the first order pressure tensor, the first order heat flux. For the diffusion velocity, we can compute explicitly all these terms because in the full BGK model, we can obtain explicitly the expression of the first order distribution function. And using this expression for the first order distribution function, we can close the equations. These equations are obtained as usual by taking moments of the kinetic equations. So for the diffusion velocity, we obtain the expected expression that we have for mixture. So we have a part depending on the gradient of number density through the Fick matrix, and a part in which we have the gradient of temperature with the Sorey coefficients in front. And for the first order pressure tensor, we obtain the usual form with the strain rain tensor with the viscosity coefficient mu, which has this form in blue. And for the heat flux, we obtain a part which is depend on the diffusion velocity, and the part depending on the gradient of T through the conductivity coefficient lambda, for which we can obtain this expression. So we were able to compute exactly all the constitutive equation. We can able to derive from the kinetic model all the constitutive equation that we need in order to close the Navier-Stokes equation. For the second regime, in which only the intraspecies collisions are dominant, at the 0 order approximation, we obtain the Maxwellian of each species. So you have a Maxwellian depending on the temperature of the species I and the velocity of the species I. And in the leading order auxiliary parameter which appear in the Maxwellian are now suitable combination of these hydrodynamic fields, which are the species fields. This leads to a system of Euler equation for the number density, velocity, and temperature of each component of the mixture. And so we have this multi-temperature, multi-velocity model, Euler equation. And an important feature is that this system is no more a system of conservation laws, but is a system of balance law. We have these terms on the right-hand side in blue, which are due to the interspecies exchanges and collisions. For the Navier-Stokes level, we obtain also the closure at the Navier-Stokes level. And the interesting thing is that, again, we have source term, which are exactly the terms, the source term that we have for the Euler equation. So at the first level, nothing changed for the source term. And for the, we have much more complicated expression for the first order pressure tensor and first order thick flux, but we were able to make them explicit, and they depend on species velocity and temperature differences, uj minus ui and tj minus ti. I skip the detail for braveness. Now I would like to present you some comparison with other BGK models. Most of the BGK model for mixture, contrary to our BGK, are based on only one global collision operator for each species. So we don't have anymore a sum of B species BGK operator, but we have only one term on the right-hand side collecting all the detail of the B species exchange, which are no more visible now. This is the philosophy followed by Aoki, Andres, and Pertam. And in their BGK, the global, the attractor of the BGK is again a Maxwell attractor, which depends on auxiliary parameters. These parameters are Ti bar and Ui bar. So we have 4 parameters for each component. So we have in total 4 and capital N auxiliary parameter. And they are determined assuming that the Wool Boltzmann operator Qi and the Wool, which is only one term now, BGK operator Q bar I, prescribe the same exchange rates for mass, velocity, and energy. So we have essentially the same philosophy that we follow in our BGK, but now it is imposed not for the B species operator, since we don't have B species operator, but at the level of the Wool collision term, from the Boltzmann level and from the BGK level. Another BGK that we propose later, we propose this BGK for a chemically reacting gas mixture, but we consider here its inert version. And it is a BGK in which the Maxwellian attractor, the auxiliary Maxwellian, depends on less parameter, because now the Maxwellian attractors are accommodated at the common velocity U double bar and the temperature T double bar. So we have in total only 4 parameters, in addition to the collision frequency, of course. And now these parameters are determined by imposing simply the conservation. So we impose that the BGK equation prescribes the same collision invariance of the Boltzmann equation. So we impose that in both cases we have conservation of total momentum and total energy of the mixture. And what we obtain with this comparison. We did some tests in collaboration with the group in Catania of Giovanni Russo, Boscarino, and Cho, who was a postdoc of Giovanni, now is in South Korea. And we use the conservative semi-Lagrangian scheme, which allows us to avoid the CFL stability condition because they are intrinsically stable. So we use these semi-Lagrangian methods coupled with diagonal implicit Runge-Kutta or BDF methods for the time discretization. And the scheme are conservative and asymptotic preserving. And we were able with this numerical scheme to to compute solution of the BGK equation. In this picture, you can see the comparison of the three BGK that I mentioned. The dotted one is the BGK, the simpler one, the one in which we only ask that the conservation are fulfilled. And the dotted one is the one that is far from the other two. While the Aoki, Andreessen per Tam, and our BBGSP BGK are very close to each other, because essentially the philosophy is the same, only with our BBGSP we have a little more detail, since we preserve in the structure the possibility to describe this species interaction. But the differences in any case disappear with epsilon not too small. So we have that all these BGK make a good job in some sense in the description of the dynamics of a mixture of inert gases. Then we compare the BBGSP model, the BGSP model, with the Navier-Stokes equation that we obtain in the limit. So we have also in this case a good agreement also for epsilon not too small. So we have some differences when epsilon is 10 to -2, but differences disappear, are not visible for epsilon equal to 10 to -3. Another test, another comparison is about the how to compare the solution from the BGK model with the solution of the Navier-Stokes multi-temperature, multi-velocity. The Navier-Stokes that we have when we consider that only the collision between a species with itself are dominant in the evolution. And we can see that the Navier-Stokes equation with the multi-temperature and multi-velocity allows to reproduce different features of the single component of each component of the gas. And we have a comparison of species velocity coming from the BGK and coming from Navier-Stokes. Again, the differences disappear with the epsilon is not in intermediate regimes. And this comparison tells us that multi-temperature and multi-velocity Navier-Stokes allows us to describe in more detail the feature of each component of the mixture. And last test that I would like to show is a test that we implement in order to reproduce, to show the SOD shock test problem in a mixture of noble gases, and we consider helium and argon, which have this ratio of masses, which is one mass is 10 times the other one. Since this approach with the multi-temperature and the multi-velocity is designed just for this case in which we have disparate masses between the component of the mixture. Here we can see that if we compare the evolution of the single number density of the two gases with the solution of the Euler equation, we have that the Euler equation classical, so with the total number density, is very close to the trend of the density of the heaviest particles. So the continuous profile is closer to the behavior of the argon component. And what happened for temperature? For temperature, we are quite far from what we have taking the global temperature, which comes from the BGK model. And in general, this picture tells us that the Euler description is closer to the dynamics of the heaviest gas, but is not representative of the lighter one. But if we take the multi-temperature, multi-velocity description, Euler description, we are able to reproduce the correct behavior, the correct in the sense of the behavior that we have from the kinetic level, both for density and for temperature. And this is possible also in where we are not not too close to the continuum limit. So for epsilon, not too small. And so in this case, with this multi-temporal, multi-velocity Euler equation, we can capture the essential features that we see at the kinetic level. So to sum up, this is the starting point from our second part of the talk. The Boltzmann model, we can recall that is based on integral differential Boltzmann equation for the evolution of the distribution function. The collision operator is a sum of binary terms. It allows a detailed description of the interaction between any pair of components, but the disadvantage is the high computational cost for integral operators. On the other hand, the BGK models are simpler linear relaxation operators. We cannot have a unique BGK model, as we can see, but they are more manageable from the numerical point of view. But this is the counterpart is the fact that we have no detail. It is not detailed as the Boltzmann model at the microscopic level. And so starting from these features, we move to define a new mixed BGK and Boltzmann model in order to combine the positive features, which are the one in blue in this slide, of the two descriptions. So we consider a model in which intra-species collision between molecules of the same component are modeled by the Boltzmann integral operators, while the interspecies collision between molecules of different constituents are described by BGK operators. So in this new model, the evolution distribution function is governed by this set of kinetic equation in which we have a part relevant to the interspecies collision, which is modeled by the Boltzmann integral, and the part relevant to the interspecies collision is described by the BGK that I have just shown you before. And so the Q tilde ij have the form that we have discussed till now. We recap here the expression of the auxiliary parameters and the coefficient of the combination that give us the auxiliary parameter in terms of the actual one. And lambda ij are related to the interaction intermolecular potentials. The first step that we move with this new model is to prove the consistency of the model. For consistency, we means that we have to prove the conservation of mass, momentum, and energy. This model conserves mass, momentum, and energy. Then we prove that he has the correct equilibrium distribution. So the collision term is 0 if and only if the distribution function are Maxwellian at a common velocity u, the velocity of the mixture, and the common temperature T, the temperature of the mixture. And the last consistency property is the fulfillment of the H-theorem. So we prove that also an H-theorem is valid for this model, and we prove that this sum of fi log fi integrals is a Lyapunov functional for the equilibrium solution. Some words about the proof of these properties. The mass conservation is the follows from this. We can simply verify that these integrals are 0, since we are dealing with an either mixture, and so there is no exchange, no max exchange. For the momentum and energy conservation, we have to prove that separately the part relevant to the Boltzmann integral and the part relevant to the BGK operator, when we take moment versus momentum and kinetic energy, are 0. To prove this, we observe that the first element of the sum vanishes because momentum and kinetic energy are collision invariant for the Boltzmann term. This is what the classical theory of Boltzmann tells us. And for the second part, we can show that this part is 0 because we have that Qij versus MIV and MIV square is the opposite of Q tilde Ji versus times MJV and MJV square. And so we have that the terms cancel out in this sum 2 by 2. And so we have the conservation laws are fulfilled by our model. For the equilibrium distribution, we want to prove that the Maxwellian are the only function that make the collision term vanish. And it is very simple to prove that if we take a Maxwellian of this kind, the collision term vanishes. For the other implication, we have first to observe that in order to make the Boltzmann part vanishes, we need that the equilibrium distribution are local Maxwellian. So passing to the weak form of the collision operator, we have to prove this, and the first part, taking Maxwellian, is 0. For the second sum, we can explicitly compute these integrals, and we obtain linear system, homogeneous linear system with not a singular matrix. And so the only solution that makes this, that we can have for this system is all equal velocity and all equal temperatures. For the H-theorem, we want to prove that the derivatives of H along the trajectory, the time derivative of H along the trajectory is less than 0. And so we have to compute this Qi scalar log Fi, the sum. So again, we separate the part depending on the part of the Boltzmann operator from the part of the BGK operator. And we substitute the expression of the BGK operator. The first part, since we have the classical Boltzmann collision operator, we know that this term is less than 0. And so for the second part, we make the computation explicit. We use some inequality that involves the logarithm. And so we can rewrite this term in this way. Since the auxiliary Maxwellian and Fi have the same order 0 moment, we have the last term disappear. And for the second term of this square bracket, we have that the minimum of this term Fi log Fi is assumed on the Maxwellian NIMI. So taking into account this property, we can obtain this last equality in which only Maxwellian appear. So we can compute exactly this moment, and taking also the logarithm of the Maxwellian distribution, we obtain this, we can rewrite this, the last expression here in this way. Now, taking into account the definition of the auxiliary temperature Tij, and also the fact that logarithm is a concave function, we can, we have an upper bound from this, we can estimate, we can from above with this sum, and from the definition of the parameter Bij, we have these symmetry properties, and we have that in this sum, we have logarithm of Tij over Ti, and also logarithm of Ti over Tj. So again, this, the terms of this sum cancel out 2 by 2. And so we obtain finally the fact that the derivative of H is not increasing along the trajectory. And in analogous way, we can prove also that the only value that make this derivative equal to 0 is the distribution equilibrium, so the Maxwellian. We do the same asymptotic procedure that we apply in the case of the full BGK operator. And so we go to study the hydrodynamic limits that we can have for this new model. With the proper scaling, we can write in a dimensional form the system of kinetic equation in this way. So we have, again, the Knudsen number epsilon in front of all parameters. And now we introduce a new parameter alpha that allows to analyze different regimes. And again, we consider the regime in which all collisions are dominant, so alpha is equal to 1, and the regime in which only the intraspecies collisions are dominant, alpha equal to epsilon. We expand again the distribution function in power epsilon up to the first order. And in the case of alpha equal to 1, so in the case of all collision are dominant, we obtain at the zero-order approximation the same solution that we have for the full BGK model. And so again, the evolution is governed at the Euler level by the classical Euler solution, Euler equation, sorry. In the case of intraspecies dominant collision, again, we have at the zero order the Maxwellian of each component, and we obtain the same macroscopic multivelocity and multi-temperature equation with the production terms that we have already seen. This is most interesting in this case, the Navier-Stokes level, because the first order distribution, contrary to the case in which we have the full BGK operator, cannot be explicitly obtained. This red term is not present in the case of full BGK operator. Now we have this LIFI1, which is the linearized Boltzmann operator, which is present due to the fact that we have a Boltzmann integral which describes the collision of one species with itself. And the other terms can be made explicit in terms of the moment of the distribution function, known moment of the distribution function. But this term is not possible to extract Fi1 from this operator. So we have in a functional form that our problem is of the type L1 Li tilde of Fi1 equal to phi I. This operator Li tilde is essentially the identity minus the linearized Boltzmann operator Li multiplied by this coefficient. And this LIH is the usually linearized Boltzmann operator with a weight MIW, which is in front of the square bracket, which is given by this expression. And it is possible to prove that under the grad assumption on the collision kernel JII, and this grad assumption is fulfilled by Hart spheres and also by cutoff inverse power law potential, and in particular it is fulfilled by the Maxwell molecules, it is possible to prove that under this assumption, the operator Li tilde is a coercive self-adjoint freedom operator on the real Hilbert space L2 with the inner product with weight Mi, and it has a trivial kernel. So it means that Li tilde is invertible and with a bounded inverse Li tilde minus 1. It means that Fi1 exists and is unique, but we cannot make it explicit. But the next step is that we don't need exactly F1, but what we need in the Navier-Stokes equation are moment of F1. So we are computing these moments in order to be able to close the Navier-Stokes equation. So in conclusion, the mixed Boltzmann-BGK model that we are studying now allows to combine the detailed description of the collision with the simplicity of the relaxation operators. It has some interesting mathematical properties that we are discovering during this study. What is interesting both for the full BGK model and also for the mixed model is that various scenarios can be obtained in the hydrodynamic limit. And as we have seen, we can have different Euler and Navier-Stokes equation that we can deduce in proper collision-dominated regimes. An interesting feature is the fact that the dynamics of mixture of heavy and light particles, and an example of this mixture, for instance, we have in plasma physics, but also in mixture of noble gases, can be more suitably reproduced in many applications by multi-velocity and multi-temperature description. A future step in this direction is the investigation of other collision-dominated regimes, like, for instance, the one in which only collision between heaviest particles are dominant, because if if we have a mixture, a binary mixture, for instance, of two components, one has a mass much more greater than the other, it is reasonable that the collision between the heaviest particles are dominant. It's less reasonable that also the lighter particle have collision dominant at the same level. So what we are, with what we intend to study is also a scenario of this kind. That's all. Thank you very much for your attention.
Ahead of time, so we have time for a few questions.
The model you have considered with Boltzmann for the same species and BGK for the other. I mean, suppose that the same, I mean, the interaction among particles of the same species is 0. So there is no Q, the Q Boltzmann. So you have an equilibrium in which what is wrong is a temperature and mean velocity, right? But there is no a possibility, instead of computing all the collision of each species system, to recover the correct temperature a posteriori. So because, I mean, after all, you have, I mean, what is dominant, what seems to me dominant when you have the same epsilon in the two part, you have an equilibrium in which temperature and mean velocity is wrong, because you don't consider the contribution of the interaction of a single species. It's correct, but I understand. So take away Q, you have an equilibrium state constructed only with the interaction of different species. So you have the wrong temperature and the wrong velocity, right? So you have to recover the right velocity and the right temperature, take into account this. So this is the question whether I understood. So maybe that one can do in a different way. I don't know.
Yes, in a different way. Yes, because in this. Oh, sorry. Yeah, sorry. Yes, because in this way you can. In all this proof, it is important that you have this.
This is the expensive part, right?
Yes, this expensive part. Yes.
Further questions? If not, I want myself. Oh.
Yes, considering the last part with the mixed scheme,
yes.
Do you think, is it also possible, perhaps you also already say that you can derive direct simulation Monte Carlo or bird algorithm based on this idea where
yes.
the interparticle doing away and the
because with the simulation of Monte Carlo, you can treat only the integral part, not the BGK part. Yes,
exactly.
But we are not two separated process, so I cannot figure out it's possible to do this, because you have no. Maybe in the case of in which the collision with interspecies collision are dominant, maybe it's possible. And it says you can separate the two steps. Yeah. Otherwise, I cannot see how it's possible to.
In that case, probably.
Yes, because the process are in the same time.
In
yes.
Competition. Yes.
In competition at the same time.
I understand. Okay. Thanks.
Other questions? No, I have one myself. I'm sorry, I must have missed that. How do you compute what is the viscosity of this mixture?
The viscosity.
Assuming this question makes sense at all, but there must be a sort of effective viscosity. If I have argon
the viscosity in this
terms which tells
we
me.
compute from, for instance, in the case of full BGK. Dominant. These are the expression of the viscosity.
That's the thing which I missed. Okay. So they are somehow related to the diagonal element of your matrix? Yes. They still are. Okay.
Yes, and depends on the collision frequency.
Okay. So
we compute explicitly.
So you have a control. You have a control.
We have viscosity and.
Okay. Okay. Any further questions? Everyone is eager to have the break. So, and I would like to finish myself since, as Maria mentioned, Giampiero Spiga was my actually first mentor back then in Bologna, and he was a marvelous person, and I would like really to take the opportunity to say hi to him wherever he is. Thank you. We are ready to go with the second part of the afternoon, which will be actually only one speaker, which is Bruce, because as I heard, Thorsten Poschel couldn't make it because of COVID. So I'm very glad and very pleased to introduce my lifelong friend, Bruce Boghosian, who has an exotic title, Exotic Distribution as Weak Solution to Kinetic Equations. Please, Bruce. Thank you.
Good. Thank you very much. I need to turn on this. Thank you very much. I'd like to acknowledge this is joint work with David Cohen of Tufts Mathematics, Adrian Devitley, formerly of Tufts Mathematics, and Sauro. I'd like to thank the Data Intensive Studies Center at Tufts who brought Sauro to Tufts 6 months ago, maybe, and that's when some of this work, the part on runaway electrons, began. I'd also obviously like to thank very much the organizers of Boltzmann Equation 2022 for all their work in organizing the conference and for the kind invitation. So this is a talk I've not given before anywhere. It's a bit of a mathematical backwater in some sense, but I also found it interesting enough that I thought that I would focus on it for one talk, and I'm also working with Adrian Devitley on one paper on this subject as well. And because I find it fascinating, and I hope you'll find it fascinating too. So I'll explain what I mean by exotic generalized distributions. The generalized distribution, that's sort of the prototypical example that we're all familiar with, is Dirac's delta. I'll do sort of a quick review of distribution theory, and then I'll turn to the heat equation and present a paradox of missing heat that will force us to introduce a different generalized distribution called the epsilon distribution. Then we'll turn our attention to another application, namely a kinetic equation for wealth distributions. And we'll see a way that that forces us to introduce another exotic generalized distribution called the Xi distribution. Finally, we'll go to runaway electrons and introduce something called the Xi2 distribution. What makes them exotic is that in a very funny way, these kinds of distributions sort of flirt with infinity in a way that will become clear as the talk goes on. Compactly supported test functions are not good enough for these. And you'll see what that means as we go on. So let's first of all look at the heat equation on R. So we have an initial value problem, which is the heat equation. We have an initial condition, that the initial condition for U at time 0 is some function we'll call g of x. And we're going to suppose that everything is in L2. We define a thermal energy. If U is the thermal energy density, then if we integrate that over all R, we get the total thermal energy, E of T. And we introduce this to students in both undergraduate and graduate partial differential equations courses. One of the first things we teach them is to show that the energy is constant. If I take dE dt, I can bring the time derivative inside the integral. I can use the heat equation to write that as the integral of U sub xx, the second derivative. You can integrate once, use the fundamental theorem of calculus, and then make the argument that because U is in L2, its derivative has to vanish at the two boundaries, and you get conservation of energy. Oops. Okay. Then we introduce to students the fundamental solution to the heat equation, which is this Gaussian, which has variance T and Gaussian in X. And that has, if you integrate that, that has 1 unit of energy. And so for all times t greater than 0, the integral of this thing is 1, and that reflects the conservation of energy we just proved. The next thing that we teach students is that as time goes to 0, this approaches an interesting object. Namely, it all piles up with 0 variance. It's all piling up at the origin. And we introduce the Dirac distribution to students. And we then go on to show that you can solve any initial value problem for any initial condition g of x by taking a convolution of the fundamental solution phi with the initial condition g. So all this is straightforward, and all of this is in elementary PDE textbooks. Let's turn a bit to what we tell students when we get to the point of the Dirac delta distribution. Historically, there are 3 ways that distributions are usually introduced. The first way is some hand-waving heuristic definition that really makes no sense when you analyze it closely. The second way is a sequential definition, and the third way is using distribution theory. So let's look at them. Dirac, I think, worked very well in the 1920s and discovered a great many things. And the first definitions of these that still appear in some quantum mechanics textbooks is that delta is equal to 0 for all x not equal to 0. The integral of delta is 1. And if I integrate delta next to some function f of x that's continuous, well-behaved at the origin, the answer is f of 0. This makes really no sense whatsoever. We all sort of imagine what it means in some limiting sense. But notice that delta, by this heuristic definition, is not defined at x equals 0, and also no such function exists. You can't have a function that vanishes everywhere except at a point, and expect that to give you an integral of 1. So then we go, and now historically, now we're in the early 1930s, we replace this by the limit of a sequence of functions. Okay, so we're going to try to define delta as the limit. Let's use the fundamental solution of the heat equation and just take the limit of it as t goes to 0. Now, what's the problem with this? Well, we write it as the limit as t goes to 0. If you prefer to think of this as the limit of a sequence of functions, we can say t is 1 over j, where j is a positive integer, and let j go to infinity. So that's this limit right here. Notice I put a question mark there because this is already dubious at this point. This limit doesn't exist when x is equal to 0. Okay, so already it's a bad definition, but that's okay. Let's run with it for a moment. If I now take this thing and integrate it next to a function f, I've got now the limit inside the integral. I'm going to do another dubious thing, and I'm going to swap the limit in the integral, which I really shouldn't do because you can do that, by the dominated convergence theorem. You can do that as long as the limit of the sequence of functions converges uniformly. This one doesn't even converge pointwise, let alone uniformly, right? Because the limit when x is equal to 0 doesn't exist. So already you got a second question mark above the equal sign there, but let's continue to run with it. That gives us this expression right here. You can see the mouse, some circuits circling with the mouse. That expression is remarkably good. That integral for any reasonable function that doesn't blow up, too rapidly as x goes to plus and minus infinity, that integral will exist. You can then take the limit as t goes to 0, and you'll get an answer. And with a little bit of real analysis that I won't go through here because you've probably already seen it, the answer it gives you is f of 0. But that sweeps under the carpet the fact that we did 2 illegal things to get to this point, and 2 wrongs don't make a right in this business. So something is still wrong here. So how is this resolved? Well, in the late 1930s, the first part of the resolution came from the Soviet mathematician Sergei Sobolev. In 1951, a great deal of the rest of the details were sorted out by the French mathematician Laurent Schwartz, who won a Fields Medal, in fact, for his contribution to this subject. In the late 1950s, British mathematician, Sir James Lighthill, wrote a book that really took all of what Sobolev and Schwartz did and explained it very nicely in a way that it could be accessible to undergraduates. Those of us of a certain age first learned about distribution theory from Lighthill's book. It really made a big difference in getting these details across to the public. So how does it work? We're going to define a linear space of test functions, and we'll call it D. These are smooth and have compact support, okay? Now, we're going to assert that delta is not really a function. What it is a continuous linear operator, and it's pairing with any function in this set of test functions. So for all test functions psi in D, the pairing of this continuous linear operator, delta, with psi is going to give you psi of 0. It's obvious that that's linear. You can show that it's continuous, but in order to do that, you have to build the idea of a norm on your space of test functions. That takes a little work, but you can do it. And so once you've done that, you've got a better definition of what delta is. And then the idea is when you write this integral over delta, what you really mean is this pairing. And so that integral is understood as an abusive notation of what you really mean is that pairing. Great. Any generalized distribution D can be defined by a continuous linear pairing of this sort. But this theory actually takes you much further. You can now define what you mean by the derivative of a generalized distribution by demanding that this be true for all psi in D. And really what this is, it looks like an integration by parts, but this now becomes a definition of what you mean by D prime. And so you're moving the prime off of the D and onto the psi in this, and you're demanding that that be true for all psi. Moreover, because psi is smooth, it's C infinity by definition, you can move as many primes as you want from the operator onto the test function. And that means if a distribution is differentiable once, it's infinitely differentiable, which is wonderful. And you can go further with this theory. Suppose you seek generalized distributions, we'll call them U, as the dependent variable of a partial differential equation. Well, you know, if you have something that has jumps in it or is sort of ill-defined at the origin like delta, you have to ask what you mean by its derivative, what you mean by a differential equation that has that as its dependent variable. Well, what you do is pair the partial differential equation, both sides of it, if you like, with an arbitrary test function, integrate by parts as many times as you need to move the derivatives off of the dependent variable and onto the test function, and then claim that what you have is a weak statement of the differential equation, which makes sense, first of all, if your dependent variable is differentiable, if it's an ordinary classical function, it's the same thing via integration by parts as the differential statement of it. But if it isn't, this statement still makes sense. And we've all seen this in, I'll give two examples here, the derivation of the Rankine-Hugoniot conditions for the jump, the shock in, for example, a hyperbolic equation rests on exactly this methodology. Finite element methods also rest on this methodology. And finite element methods, the test functions are typically a finite set of 10 functions or something like that you would use. Okay, so now that we're happy with deltas, initial condition of a delta for the fundamental solution to the heat equation, let's return to the heat equation. And although it receives much less attention, let's look at the t goes to infinity limit, not the t goes to 0 limit, but the one you might think was the easy limit, t goes to infinity of phi. I would argue that this is even more troubling than t goes to 0. Why? Well, because we've already shown that for all t greater than or equal to 0, you can even throw in equal to 0 because we now understand the delta, the total heat energy is 1. But now you also have the limit as t goes to infinity of the fundamental solution. If you think about that Gaussian for a moment, the limit as t goes to infinity of it is 0. And more worryingly, it's 0 uniformly. And that means I can swap the limit in the integral in this case. So I know that, you know, if for all finite time the answer is 1, well, then the limit as t goes to infinity of this thing will be 1. And if I can swap the limit in the integral, then I can bring the limit inside. But this limit, we've just said, is 0. And the integral of 0 is 0. Okay, so there's a paradox going on here. What happened to the 1 unit of energy? And remember that in this case, it really is legitimate to swap the limit in the integral by Lebade's dominated convergence theorem. All right. I would have thought that this thing would have been answered in classical literature, but the earliest addressing of this question that I'm aware of was pointed to me by my colleague Francois Dubois in Paris. He pointed me to a paper by Robert Vallée from 1992 called the epsilon distribution, or the antithesis of Dirac's delta. Vallée was a mathematician and cyberneticist who was heavily influenced by Schwartz and also by Norbert Wiener. Here's the intuition. If delta describes a distribution that's sort of infinitely tall and thin with integral 1, epsilon describes a distribution that's infinitely short and fat with integral 1. Now, the infinitely short and fat means that it ought to uniformly converge to 0, but we're saying it has integral 1. Now, how can we justify this? Well, the heuristic definition for the limit as t goes to infinity of phi would be a distribution that's 0 everywhere on R and yet has integral 1. Vallée's text, which was written in French, he described it as presque rien, which means almost nothing, essentially. It's not quite nothing because it integrates to 1, but its heuristic definition, I would argue, is even more absurd than Dirac's heuristic definition. The sequential definition would be the limit as j goes to infinity of phi and x and j. The trouble is this converges uniformly to 0. So that doesn't work in this case either. The epsilon distribution really illustrates the inadequacy of both the heuristic and the sequential definitions even more starkly than the delta distribution does. Once again, distribution theory comes to the rescue. But this time you have to go a little bit further than the smooth, compactly supported test functions. So you have to expand the space of test functions and allow for test functions that are not compactly supported. Because for all compactly supported test functions, for all phi in the space of compactly supported test functions we've already described, the pairing of epsilon with phi is going to be 0. Right? You've got this thing that's getting shorter and fatter integrated times something that has compact support. Well, you know, eventually the answer is 0. So this is not good enough. What we need to do, and much more could be said about this, but I just don't want to get into the weeds of the mathematics here. What you can do intuitively is define a new space, a bigger space of test functions. We'll call it d sub epsilon. And this is the set of all functions that are smooth and for which this quantity exists. And this is like the average of psi over the entire reals. So now this includes things that are not compactly supported, like, for example, a constant function, right? It includes periodic functions, right? So 1 plus 1/2 cosine t or something like that. Fine, we can integrate, we can pair that with epsilon. almost periodic functions. In fact, if you try to characterize exactly which functions this works for, it's a little bit difficult to do. But hopefully that conveys the idea. We then define the pairing as, okay, for all psi in this new set of functions, d sub epsilon, the pairing of epsilon with psi is precisely this object, this average over all the reals. Again, I'm going to say that you have to, in order to make this work, in order for it to be a continuous linear functional, you need to be sure that you have a norm on your space of test functions. You can do it. It's a bit more work, but you can still do it. Okay. So now, with the epsilon distribution in hand, we're going to try to go back and resolve the heat paradox. And what I want to do is, if we're talking about continuity at infinity, whatever that means, we're bothered by the fact that this thing is 1 for all times. Its limit as t goes to infinity is 1. But if I bring that limit inside the integral, in other words, if I convolve it with the limit of the fundamental solution, I'm getting 0. So we need to talk about what's going on, not just as you approach infinity, but at infinity in some sense. And so what I'd like to do is extend the time domain to the extended positive reals instead of just the positive reals. So I want to look at time being positive reals or time being plus infinity. So, all right, we can do that. And now what I want to claim is that the fundamental solution to the heat equation at t equals plus infinity is the epsilon distribution. Now, how does this work? Remember that an arbitrary solution to the heat equation is the convolution of the initial condition with phi. If I now evaluate both sides of this thing at t equals plus infinity, I'm getting u as x goes to plus infinity is this, right? Where I've now replaced phi by epsilon here. And I've got the first argument now of phi. I can now integrate this equation over x on both sides. I have to swap the order of integration on the right, but that's fine. The integral of the epsilon will go to 1, and you will get this, which states that at t equals plus infinity, the total heat energy is exactly what it was in the initial condition. And so using this epsilon distribution, you actually can demonstrate this idea of conservation of energy at an infinite time, and the paradox that I described earlier goes away. Okay, deep breath. Now, the next chapter in that, so epsilon is really the first example of what I'm calling, yes, of course.
What you just said, remark, the Cornus periodic function in the sense of physical.
Well, as I did mention, almost periodic functions are valid test functions for epsilon. I'm not an expert on that, but I'd be happy to discuss it with you afterwards. Yeah, but yeah, those are valid functions that you can apply epsilon to. What really matters is that integral exists, and at least with the Besekovich definition, that integral will exist for that case. So, right. So let's move on then to wealth distributions. If epsilon is the first example of a exotic generalized distribution, wealth distributions raise different problems. So these are ideas that come out of work on what's sometimes called econophysics that goes back to the 1990s. You try to replace your molecules with economic agents. Instead of colliding with each other, they transact with each other. Instead of exchanging energy in their collisions, they exchange wealth in their transactions. You write a Boltzmann equation for it, and you analyze it. The work on this subject goes back around the 1990s. There were seminal papers written at that time by Ispolitov, Krapivsky, and Redner was one of the papers. Viktor Yakovenko is another one, and there's a wonderful book on this subject by Professor Toscani as well, with a chapter on these kinds of wealth models. So let's suppose, for the moment, let's suppose that wealth is always positive. We won't go into agents that have negative wealth, even though there are some models that include them. I'm going to sort of sweep the negative wealth issue under the rug for the purposes of this talk. So P of W is the agent density function. So the integral of P of W between A and B is the number of agents with wealth between A and B. And we're going to suppose that again, this is in R plus. The total population of agents, the total number of agents is capital N. The total amount of wealth contained in the society is capital W. N is the 0th moment of P, capital W is the first moment of P. You can also define an intensive variable, which is the mean wealth of capital W over capital N. We'll denote that by mu. Before going on to see what kinetic equations in this business look like, I want to describe another way of specifying what the distribution is. And this goes back to work in economics by Max Lorenz, an American economist who actually did what I'm about to describe in his PhD thesis at the University of Wisconsin-Madison back in 1905. Let's define two functions. I'm going to call the first one L. And if you look at its definition, it is the fraction of wealth held by those agents whose personal wealth is less than little w. And then I'm going to define F, which is the fraction of agents whose personal wealth is less than little w. And I'm going to plot a parametric plot of L versus F. So in other words, I've got the fraction of wealth held by those agents with wealth less than W versus the fraction of agents held by those agents with wealth less than W. You can fairly easily prove, it's like a calculus 1 exercise, that this curve has to lie below the diagonal and it has to be concave up. It doesn't necessarily have to be monotone increasing, but if you only have positive wealth agents, it will be. If you have negative wealth agents, it could decrease at the beginning. So let's look at some examples of this. This blue diagonal here, suppose you had a society where everybody had exactly the same amount of wealth in their pockets. Then a quarter of the population would have a quarter of the wealth, half of the population would have half of the wealth, etc. It's always going to be true that 0% of the population has 0% of the wealth, and that 100% of the population has all the wealth. So it'll always start at 0, 0 and end at 1, 1 in the unit square. If everybody has the same amount of wealth, it's just the diagonal. If they don't, if there's inequality in the society, this curve has to lie below the diagonal. And again, that's not difficult to show. It's pretty clear that the bottom 40% of the population is going to have less than 40% of the total wealth. It's, again, not difficult to prove upward concavity as well. Let's go to the opposite extreme. Suppose you have an oligarchy. One person has all the wealth, everybody else has nothing. Then the curve flatlines all the way across until you get to the very last person, at which point it sort of discontinuously jumps up to 1. or at least in the limit of infinite population, it discontinuously jumps up to 1. So now it's this orange curve here. There's a third possibility that's interesting. I mean, you can get, curves that start at 0, 0 and go smoothly up to 1, 1 and lie below the diagonal. But there's a third interesting singular possibility, and that is that the curve goes up and hits the right-hand side below the diagonal and then discontinuously goes up the rest of the way. And that's called a partial oligarchy, because what it means is that a fraction of the population that is nearly 0 has a finite fraction of societal wealth. Okay, and that is the case in real empirical studies. At least it's a better approximation of the case of the empirical data than most other things you can come up with. Because, for example, in the United States today, the richest 400 households have as much wealth as the bottom 60% of the population. That's 400 people who have as much wealth as 200 million people. Alternatively stated, that's 0.00012% of the population have as much wealth as the bottom 60%. That is much closer to a partial oligarchy, a discontinuous jump up at the end of the Lorenz curve, than it is to almost any other distribution you can think of. So we need that. And the Lorenz curve shows it in a way that no plot of the PDF will ever show it. Lorenz actually had a very clever idea for pointing out a pathology of the distribution, a generalized function in our terminology that you couldn't see just by looking at a PDF, looking at the tail of the PDF. Let's take a deeper dive at looking at what's going on out on that tail. What does the PDF look like for that jump of the Lorenz curve at the end? Let's look at a total oligarchy for the moment, rather than just a partial oligarchy. Let's suppose one person has wealth W and all the others have wealth 0. Well, great, I can write down what the PDF of that is. I've just got n minus 1 times delta of W corresponding to n minus 1 people with wealth 0. And I've got one person that has the total wealth of the society, and that's reflected by this delta. Now, suppose I want to take a continuum limit. I want to let the population effectively go to infinity. Well, in that limit, I have to fractionalize people, right? I have to talk about a half a person and a third of a person and a fifth of a person. Good, so we can talk about n minus 1/2 people that have wealth 0, and a half of a person that has wealth 2W, right? Because we want the total amount of wealth in the society to still be capital W. Or you could have n minus 1/3 people have wealth 0, and 1/3 of a person have wealth 3W, etc. You could have n minus epsilon people have wealth W, and epsilon of a person have wealth W over epsilon. This is the continuum limit that we're really taking when we want to talk about oligarchy. All right, let's let epsilon go to 0 and see if what mathematical object do we end up with as epsilon goes to 0. If we replace epsilon by capital W epsilon, and we still let epsilon go to 0, it's the same limit, we can write it like this. And the virtue of this is now the capital W appears out here next to this mathematical object. The limit as epsilon goes to 0 of epsilon times delta of W minus 1 over epsilon. Now, you might want to say this is 0 because there's an epsilon sitting out there, but that's dangerous, and we'll see why on the next slide. I want to call this object Xi of W. We call it the oligarch distribution. What we've got now is that the PDF corresponding to a total oligarchy is n people that have wealth 0. N people because there is essentially, epsilon went to 0. There's no people tied up in this term here, only wealth. And this object, C of W, is this limit. If you prefer to think of it as a sequence, again, replace epsilon by 1 over j and take the limit as j goes to infinity. If you look at this object here, as j goes to infinity, first of all, its 0th moment is 0. If I integrate this over all w, the delta will integrate to 1. I'll be left with 1 over j as j goes to infinity, that's 0. But what about its first moment? If I multiply this by w and integrate over all w, well, then I'm going to get a j from the integral because I've got delta of w minus j times w integrated over w. That j will cancel with the 1 over j, giving me 1, which doesn't depend on j. So as j goes to infinity, I get 1. Higher moments of this thing don't exist, but the 0th moment is 0 and the first moment is 1. In other words, if delta is 1 unit of people where there is 0 wealth, C is 1 unit of wealth way out on the tail where there is 0 people. It's sort of the, sorry? Well, yeah, there's a fraction of people that is going to 0 possessing 1 unit of wealth. That's the idea behind the Xi distribution. And then the real PDF that we have is this, and this will have the correct 0th moment and first moment. If I take this P defined in this way and I integrate it to get its 0th moment, the answer is n. If I integrate to get its first moment, right, I multiply this by w and take its integral, that gives me 0 because it's the integral of delta w times w. But this gives me, that integral will give me 1 and the answer will be capital W, which is correct. So this is the object that we would like to understand. Let's go through the heuristic, sequential, and distribution theoretical definition of this object that we've motivated here. The sequential, well, that was the heuristic. The sequential approach to Xi is let's do it again with the fundamental solution of the heat equation. You could do this with essentially any function that you like, and you'd get something similar. We've got something that integrates to 1. We'll use phi. It's centered at w equals j. Yeah, I can point to it down here. And its characteristic width is 1 over j. And its amplitude is then 1 over j. And this is the object, and I'm putting, quotes around the equal sign because the sequential approach really is not good, but let's go ahead with it anyway. You can see this sequence of Gaussians that's getting smaller and smaller. The amplitude is going as 1 over j, getting narrower and narrower because the variance is going as 1 over j, and shifting further and further out, centered at w equals j. The pairing of this with 1 will give you 0, as we've seen. The pairing of this with w will give you 1. Okay. Can we, once again, can distribution theory come to the rescue? The answer is yes. First of all, notice that for all phi, not only in D, but in D sub epsilon, the answer is going to be 0. If you don't want to get 0, you've got to hit it with a test function that's increasing linearly with w. Right, so we see the example on the bottom of this slide that the pairing of C with W itself is 1. You need, at the very least, and I'm not pretending to characterize these sets of test functions exactly, you need everything that was in D sub epsilon, but you also need terms that are proportional to W. And what the action of C is to pick out the coefficient of W. It returns alpha. It returns the coefficient of W. It just looks at anything that increases faster than linearly, you won't be able, is not in the space. But if it increases linearly, then the coefficient of that linear term is the answer when you pair Xi with it. Again, you really have to take care to choose a norm on this space of test functions. That is a minor nightmare, but it was done. I didn't put the publication here, but it is in print a few years ago from Adrian Devitt-Lee. Let me go a little bit into what a kinetic equation for this might look like. And I'm going to give the example of something that we call the extended yard cell model, which is an extension of an idea that came from Anirban Chakraborty at the University of New Delhi back in 2002. Let's suppose we have two agents whose wealths are W and X, and they engage in a transaction in some characteristic time delta t. We're going to say that the amount of wealth that they exchange is going to be proportional to the square root of delta t, as you might expect from a random process of this sort, times the minimum of the two wealths. Now, why the minimum? This is meant to capture a certain amount of loss aversion or risk aversion. Nobody wants to go broke. Everybody basically gambles in every transaction a small fraction of their own wealth, right? If I enter a transaction with Bill Gates, chances are the thing that is going to be exchanged is going to be a laptop and not a yacht, right? It's going to be a fraction of my wealth and not of his wealth. So that's where this minimum of WX comes from. But we are going to say that which direction it goes in, this eta here, could be either direction. That eta could be plus or minus 1. The simplest thing that you could do is to flip a coin with even odds to decide in which direction it goes. And that would mean that the expectation value of eta would be 0. But we're not going to do that because in real life, wealthier agents have an advantage. They get better financial advice. They get better return on investment. You can make a litany of cases that wealthier agents have advantages in society. We're going to capture that by making the expectation value of eta proportional to W minus X. Remember, this is written for W, this is written for delta W. Well, if W is greater than X, in other words, if W is the wealthier agent, this expectation value will be greater than 0 and W gets the advantage. If W is the poorer agent, this expectation value will be a little less than 0 and W is at a disadvantage. The other thing we're going to add to this model, and by the way, we're introducing a parameter zeta, which measures this amount of wealth attained advantage, as we called it. So if zeta is 0, there's no wealth attained advantage. In real societies, zeta tends to be positive. The second thing we're going to do is redistribute some amount of wealth, because if we don't, you end up with a total oligarchy in these models. But we prevent that from happening by taxing everybody proportionate to their wealth, putting all that wealth in a pile and returning it to everybody in equal shares. And what that has the effect of doing is compressing everybody toward the mean. And wealth distributions are incredibly skewed, so there's more people moving up than down. Right now, in the United States, I think the median wealth is about $100,000 for a household. The mean wealth is more like $750,000 for a household. When I teach probability and I want to teach students the difference between median and mean, this is the example I usually give. It's so skewed, thanks to very wealthy agents, that 85% of the population of the US are below the mean, and they would actually receive money under this redistribution. It's the top 15% that would come down a little bit. So now we have a two-parameter model. The parameters are xi and zeta. And this model, as simple as it is, and easy as it was to motivate, and I've explained, this model to high school students who have then gone and written computer programs, actually describes real wealth distributions reasonably well. The first thing that you can do is derive a Fokker-Planck equation for it. And it looks like this. Sigma, the drift coefficient, is this. Notice that the drift and diffusion coefficients involve the dependent variable, so it's nonlinear. And in fact, they involve integrals over the dependent variable, so it's non-local as well. But you can still deal with this equation numerically. And it gives you a two-parameter solution set. It also exhibits weak solutions that correspond to partial oligarchy. It exhibits solutions that looks like this top line. P is given by a classical function, little p, plus some fraction of the total wealth, capital W, times our oligarch distribution. And these things are weak solutions to the Fokker-Planck equation that I just showed you. You can do an interesting thing with this. Because these are two equivalent descriptions, you can take the Fokker-Planck equation we've written for capital P and tease it apart into two equations, one for little p, which we call the wealth distribution of the peasantry, and one for C of t, which is the fraction of wealth held by the oligarchy. You get a partial differential equation for little p, the wealth distribution of the peasantry, and you get an ordinary differential equation for C of t, which is the fraction of wealth held by the oligarchy. So when you go to this representation, it naturally gives you two coupled equations. What does the Fokker-Planck equation for P, little p, the peasantry, look like? Remarkably, it is identical to the equation for capital P with a few changes. Obviously, you replace capital P by little p. You replace xi by xi divided by 1 minus c. You replace zeta by 1 minus c times zeta, and you have to add a time-dependent term to the drift coefficient. Once you do that, you've got an equivalent definition that just doesn't involve any generalized functions anymore, generalized distributions. It just is a coupled PDE with an ODE. And also remarkably, the ODE for C is a logistic equation. And it has two solutions, one where C is 0, two steady state solutions, that is, one where C is 0 and there's no partial oligarchy, and one where C is 1 minus chi over zeta. The stable one is C equals 0 if wealth attained advantage coefficient zeta is less than redistribution chi, then there's no oligarchy. In other words, if your redistribution is sufficiently large, larger than the wealth attained advantage, you will prevent oligarchy from happening. If zeta is greater than chi, then this fraction here is less than 1, and C equals that is then your stable solution for the fraction of wealth held by the oligarchy. So the formation of oligarchy is in fact a critical phenomenon. And you can just reflect on historical events like the collapse of the Soviet Union in 1991, where redistribution dropped dramatically and wealth attained advantage increased dramatically, thanks to some of the corruption that was going on at that time. And that triggered a phase change under which, in the course of 10 years, 15 countries that had previous to that been socialist republics became oligarchies, or at least 12 of the 15. That kind of thing can be thought of as a phase transition in this sense. So we have a subcritical case where zeta is less than chi and you get a classical solution with no partial oligarchy, a supercritical case where zeta is greater than chi and you have an oligarch wealth fraction of 1 minus chi over zeta. And a very interesting thing about this is it exhibits a phenomenon that physicists call duality, similar to the Kramers-Vannier symmetry of the Ising model, if you're familiar with that. If you invert this quantity, if you exchange chi and zeta, obviously you'll go from a supercritical state to a subcritical state, a state with oligarchy to a state without oligarchy. Under that change, the wealth distribution of the peasantry will be invariant. The shape of it won't change, which is a remarkable non-trivial symmetry of the equations that I just showed you. You can see in these numerical simulations, the phase transition. This is done for redistribution chi is equal to 0.2. As long as zeta is less than 0.2, this group of curves up here, the Lorenz curve goes up to 1, 1. There's no partial oligarchy. When zeta is greater than that, the Lorenz curve ends on the right-hand boundary, and you do get a partial oligarchy. So the solution set for these equations include both partial oligarchical and non-partial oligarchical solutions. And we can go ahead and try to fit this to empirical data. The red curve here is empirical data for the United States in 2013. That's what the wealth Lorenz curve looked like. The blue dashed line is a solution to the system that I just described to you. And the error, the L1 difference in the two Lorenz curves is less than 0.25%. And you can do the same thing over other time epochs in the United States. And then we got data from the European Central Bank, and we tried it for Austria and Germany and a bunch of other countries. And it works reasonably well. Somehow it works slightly better for the US than other countries, but it's still pretty good. One interesting point is that most countries are actually near criticality. So it seems that inequality increases until this criticality is achieved, and then it sort of floats around the critical point. My final thing, Sarah, tell me, and I have 5 minutes. Well, I'm not going to take, I don't want to take advantage of that fact, but let me just finish with a bit of plasma physics, runaway electrons. Tokamaks confine plasmas in a toroidal chamber, toroidal vacuum chamber. There's a big one being built in the south of France. And it's very, very big. The cost of it ranges from anywhere from $18 billion to over 50 billion, depending on whom you ask. When it's finished, it will be the biggest tokamak by far ever to have been created in the world. In the middle of this chamber, this toroidal vacuum chamber, is a solenoid. If you pulse electricity through the solenoid coil, it will obviously pulse a magnetic field through the middle of the torus. By Faraday's law, that will induce an electric field around the torus. The electric field will drive a current in the plasma. It will drive the electrons in one direction and the ions in the opposite direction. The electrons, however, move much faster because they're much lighter. And you might model this by considering moving electrons in a stationary neutralizing background of ions. Now, there are very many sophisticated models of this. Being a mathematician, I'm going to try to strip this down to illustrate the point that I want to make without keeping all the details. For one thing, you really need to do this relativistically, because the rest mass of the electron is just a mere 511 kiloelectron volts. And these things go much faster than that once you get them going. And the reason that they go faster than this is because of an interesting feature of electron collisions in plasmas, and that is that as their speed increases, v, the electron collision frequency will decrease like 1 over v cubed. And that means that once they get going, there's almost nothing stopping them at some point. The faster they get going, the more they run away. And so an increasingly small fraction of electrons will start rocketing up to higher and higher velocities. And the result of this in the real world is something kind of like a lightning bolt coming out of the plasma and hitting the inside wall of the vacuum chamber that is probably worth hundreds of millions of dollars. And so people would like to know how to stop that from happening, how to control the plasma well enough so that they don't enter a regime where this happens. And once again, there's probably a critical point above which it happens and below which it doesn't happen. And they would like to understand that well. We're going to sweep this away and just kind of focus on how this might relate to generalized functions of this sort. First of all, we're going to treat this non-relativistically. We're going to use a linear kinetic equation that's due to Fish in this article that actually Sauro pointed me to in Reviews of Modern Physics in 1987. The idea is this is a kinetic equation for a weakly turbulent plasma, but spatially homogeneous. And if that sounds like it's a contradiction in terms, that's because we're averaging over the turbulent length scales. So it's like a turbulent average plasma. I need to get the exact reference from you. But it is quoted, at least, in Fish's article here. Yeah. Yeah. Yes. Okay, so this is what it looks like. And once again, it's a Fokker-Planck equation. E is the electric field. The collision frequency is modeled by this gamma of V, which, is dominantly 1 over V cubed, the magnitude of V cubed. Now, the energy of the plasma would be the integral of F integrated against V squared over 2. So we're just using the non-relativistic kinetic energy here. What we want in order to see what's happening in terms of exotic generalized functions is a new generalized function. I'm going to call it Xi sub 2 that has 0th moment equal to 0, first moment equal to 0, but it can pick out the kinetic energy. So we'll say its second moment is equal to 1. Okay, this is modeling an infinitesimal fraction of electrons moving at infinite speed in such a way that they contain a finite fraction of the plasma's energy. So a distribution theoretical treatment would need to, I'm not going to go into the test functions, but by now you get the idea. This will include test functions in D sub epsilon, plus not only linear terms in W like we did for Welf, but also quadratic terms in W. And Xi2 will just extract the coefficient of the quadratic term. How do you tell if you have data from a numerical simulation of this PDE that you really have any Xi2 in your data? I shouldn't touch the podium. Well, in this case, I think we can take a lesson from Lorenz. This is actually a case where we can transplant an idea from economics to physics instead of vice versa, which is the usual direction. L of V is now going to be defined as the fraction of energy held by all electrons with velocity less than V. And F of V will be the fraction of electrons with velocity less than V. And we can work that out from the numerical solution to this equation. This will give us a sort of Lorenz curve for electron energy. So fraction of electron energy on the vertical axis and fraction of electrons on the horizontal axis. In this case, because it's a second moment and not a first moment, the properties of the Lorenz curve are in fact swapped. This is guaranteed to be increasing, monotonically increasing. It is not guaranteed to be concave up. Okay, so now I need to show you this, and I'll finish with this. Let me see if I can do that. Okay, so yeah, this is what it looks like. We're starting with a distribution of electrons, and this is velocity. We have an electric field that's going to push them in the positive direction. This is the Lorentz curve. Again, it doesn't have to be concave up. It does have to be monotone increasing. And sure enough, it's pushing you. It's hard to do this simulation past a certain point, but it's giving you sort of an oligarchy of electron energy. This thing runs, and it is presumably going to a case where an infinitesimal amount of electrons are holding a finite fraction of the total energy. A little bit different from the wealth example. For one thing, energy is not conserved in this case because we're applying an external electric field. So in conclusion, exotic generalized distributions go well beyond the Dirac delta in mathematical sophistication and utility. I think you can see now what I meant when I said they sort of flirt with infinity. And this is what makes them a bit difficult to deal with and to develop test functions for. They can be described with distribution theory, but they require spaces of non-compactly supported test functions. They enable the extension of the domain. We saw the case to the extended reals. We've also used, and it actually makes the derivation simpler, non-standard analysis where you have real infinitesimals and real infinite numbers. It's another way of doing it. They appear as weak solutions that typically describe what I would characterize as breakdown phenomena. I would call the formation of oligarchy sort of a breakdown in the evolution of a wealth distribution. Runaway electron lightning bolts coming out of plasmas is a breakdown of what's happening in the plasma. We saw 3 examples of this. These things can also be described with other methods of functional analysis. And that includes non-standard analysis. It also includes extensions of measure theory. They're mathematically interesting objects, and it's, to me, I find it interesting that real-world problems like this can really get at the boundaries of both functional analysis and real analysis. I thank you very much for your attention.
I think we still have maybe some time for a few questions. We are a little bit behind schedule, but there is no schedule left at this point. So I think as long
sorry if I went over.
As long as there are questions.
Thank you very much for a nice talk. It seems to me that what you are dealing with is what physicists would call condensation.
Yes.
In the sense that the most simple example with Bose-Einstein condensation.
Yes.
But there are other examples in other fields, right? So it's the same thing.
That reminds me to bring up a paper that I should have referenced when I was quoting the econophysics literature. A wonderful paper by Jean-Philippe Bouchot,
yeah,
from 2000. They refer to this as well.
Yeah. And I mean, in a sense, it seems to me, I don't know if I'm right, but this Lorentz plot, it looks a bit like the same that you do when you want to, within this large deviation theory, you want to find the saddle points in order to check if your large deviation function has indeed a non-analyticity point that corresponds to condensation. I don't know if you've ever, if I'm correct or not. Typically, condensation can be seen in the large deviation theory, as far as I know, as a non-analyticity point of the large deviation function. And usually this you find by some saddle point construction. And it reminds a bit of the same construction that you do when you have a finite intercept of the Lorentz curve. I don't know if there's some relation or not, but superficially it looks very similar.
I have to think about it, but that sounds very right. Yeah, I'd love to discuss it with you, in fact.
Yeah,
afterwards.
just a last question. From a practical point of view, constructing these Lorentz curves from a simulation, as you did, I mean, does this suffer from statistical error? Because typically this is something viable for, let's say, a generic distribution.
So I didn't use Monte Carlo to do that. I actually did a simulation of the Fokker-Planck equation itself.
So you solved the probability distribution.
I solved it numerically.
Okay.
Now, once the distribution becomes too extended, it becomes numerically very difficult to do it. Yeah, when you get a long tail. I've got a particle method is one way of doing it. But once the tail becomes long enough, you have to split particles and annihilate particles in order to put the computational resources where they're most needed to describe the distribution. And it becomes very difficult to use particle methods. Almost anything like a finite element method for the PDE would require an enormous domain, and for most of the time you would only be using a small fraction of it. It's difficult to do numerically. But I think what you're saying is right. I'd love to discuss it some more, in fact, yeah.
Any further question?
Can you explain these wealth distributions in terms of some dynamical model?
Well,
what you've done is purely descriptive. There's some underlying phenomenon which will give rise to oligarchs and some dynamical model which will give rise to some kind of egalitarianism.
Yeah, well, yeah.
Microscopic theory, as I understand.
The Fokker-Planck equation that I showed that was derived from that extended yard sale model does describe a wealth distribution according to that model. Now, I gave this talk once, and it was in a country that had a very unequal wealth distribution. And I was asked, what do we have to do to change the wealth distribution? This model, of course, is very simplified with only two free parameters. The real answer is you increase redistribution and you decrease wealth attained advantage. By decreasing wealth attained advantage, you make the playing field level for everybody. You don't give wealthier agents an advantage in the outcome of the transaction. And then you can then increase the redistribution as much as the society would like. Ideally, this would be done by a democratic process, and society could decide, you know, how narrow they would like the distribution to be. I think from a political point of view, the world is a long, long way away from any procedure like the one I just described. But those are the two things you have to do. So I said in answer to the question, well, you need to increase redistribution and decrease wealth attained advantage and inherent corruption. And the answer was something like, tell us something we don't already know.
Just one final point. With regard to the oligarchy in Russia, how stable is that in the context of your model?
Yeah. Unfortunately, oligarchy is extremely stable if the one, well, as you would expect, if you're far supercritical, so zeta is much greater than chi, the oligarchical fraction of wealth is large. I would point out in the United States today, it's about 30%. Under those circumstances, you're far away from criticality, and that equilibrium is very, very stable. If you could get it close to criticality, it would destabilize, right? You would end up with a transcritical bifurcation right at criticality. So as you approach criticality, it would become less and less stable. And that's why I find it interesting that a lot of countries are sitting right near criticality. Most slightly above criticality. Most countries have a small oligarchy. The United States has a big one. It's about, and The other thing that this methodology allows you to do, if the solution space to this equation includes some weak solutions with partial oligarchy, as well as classical solutions, we fit to the Lorenz curve. And if the best fit involves a partial oligarchy, that's what we have. If the best fit doesn't, then we don't have an oligarchy. In other words, the procedure provides a sharp mathematical distinction between the wealth distribution of an oligarchy. From empirical data. You can say this country is an oligarchy, this country isn't. And it's not a matter of opinion. It's not a matter of just estimating the steepness of the curve. It's the best fit to the model is a weak solution. So there are some advantages to actually having an underlying model. It removes that kind of subjectivity.
No, very nice. Several comments which I would like to make, but I will make them later. Just one remark on what we are discussing now. One strong point of Bouchot and all these models of wealth inequality is that there is no merit in getting rich. It's a result of pure randomness. So I think you should tour, you and Bouchot and so on, all business schools and destroy what is. Yeah, but it's very important that that people get the message. I mean, because it's a main obstacle towards redistribution. I mean, it's in your game it's very clear, right? I mean, it's you clear, just have a random variable which you will fix the expectation, and that's what.
I mean,
yeah. Anyhow, well, yeah, no.
Beinhocker has a book called The Origin of Wealth, and he makes exactly this point. You know, economists, according to neoclassical economics, economists believe that everybody has a utility function in their head, and they act according to that utility function to increase their utility in every transaction. And if their outcome isn't favorable, if they end up poor or in ruination, they say, well, that's because of your utility function. It becomes a convenient trope for blaming people for their state in society. And what Beinhocker points out, which is, I think, the point you're making.
You can even have a utility function, because in your model, when you say that you take the minimum of the two wealths and you take a fractional proportion, that's Kelly betting. I mean, if you assume that it's a matter that you may get the expectations wrong, and that is so easy because there is so much noise, right? So you may even be a utility maximizer with a logarithmic utility.
That's right.
And nevertheless, your model would work. And
you can,
just because one of the two parts doesn't understand that it's that is not going to gain. But this is very easy to make.
That is, yeah, no, it's right. Beinhocker's punchline is saying that wealth differences between people are due to intrinsic differences in them, right, in their utility function, would be as absurd as saying in physics that I have a container of argon atoms and they have a Maxwellian distribution. And the reason that some of them are moving fast and others are moving slow is because the argon atoms are different, right? Argon atoms are as identical as any two things in this universe could possibly be. And Beinhocker makes the point. That argument, as ridiculous as it sounds in physics, passes for valid in neoclassical economics.
I'm sorry. I'm not an expert at all, but you cannot deny the personal merit, after all. I mean,
there's surely a correlation.
Set it to zero. Where is it here?
People are different, and there's surely a correlation.
Where does it reflect?
But even if there weren't a correlation, you would see this kind of wealth distribution. The correlation only makes the inequality worse.
You understand that? Okay, it's a very good topic. Any further? Angelo, you're silent on this inequality. By the way, Bruce has a very beautiful paper on Scientific American, which was targeted to the economists. What happened with that? Did they? Probably they don't want to hear this. I don't know.
people who identify themselves as heterodox economists do engage in this, and they're thoughtful and they're interesting, and I've talked to a number of them. But then there are people that just wrap themselves in sort of orthodox neoclassical ideology, and I can't penetrate that crowd.
So thank you for the interesting talk. Let's come back to neutral mathematics. My question is simply a curiosity. If there's a generalization of this distribution, in the case in which in the space you put like exponential or more than exponential
instead of just powers of W.
Instead of that, yes, instead of powers.
There surely is, but we haven't investigated it at all. And I have hunted for this kind of thing in the literature. I think maybe the closest thing is, literature on condensation and so forth, but it's hard to bring it all together in from the literature. But yeah, there's got to be. Yeah.
Okay, thank you.
Okay, looks like this is topic deserves more discussion. Anything for the next? Well, we still have some time tomorrow with I don't know whether Giuseppe will be related to this somehow. Maybe yes, maybe not. Okay. Due to your age, okay. Okay. So anyway, we can go as long as we wish to, but
utility part is good if you know the complete situation of the market. But since you don't know exactly, it's not, but then you can use people.
Yeah, there's a bunch of assumptions that are built into neoclassical economics. Symmetric information is one of them. There's a list of them. You can buy insurance for any eventuality. There's always a buyer for every seller. And most of them are wrong. And it's interesting that heterodox economic theories, like, for example, George Akerlof's work on asymmetric information, start by questioning these assumptions. Work on dynamic stochastic general equilibrium is a modification of general equilibrium that allows for stochasticity. There's other examples of this as well. One obvious one is Kahneman and Tversky's prospect theory, which assumes that there's no utility function at all. There's a value function that's very different. And that started from something called the Allais paradox back in the 1960s, I think, that psychologists just can ask lots of questions to groups of people. Would you take this bet? Would you take that bet? And you can very clearly tell from the Allais paradox, if you try it on a group of people, as small as the number in this room, I can't do it off the top of my head, but just ALLAIS, there's a Wikipedia page on it. People will answer yes to this question, which sets up one inequality for the utility function. And they will answer no to this question of, would you take this bet? And that sets up another inequality for the utility function. And the two inequalities are contradictory. The solution set is 0. So we don't think in terms of utility functions. But interesting stuff.